on processing research data with artificial intelligence, even if we heard of talking about artificial intelligence in all sessions, I think. But okay, I have only 10 minutes, so let me go fast to my introduction, the AI landscape and roadmap in AGI. Here is an introduction, no time to go through the whole dots of this brief history of what happened in the last years, but I try to go back to the last two AGI conferences, to my introductions. So in 2022, that was before ChatGPT, there was still two big communities in AI. That was the computer vision, processing images and videos, and another big community in processing text, so doing natural language processing. They do not talk among them so frequently. And I presented a first AI landscape analysis of the tools and framework available at that time. But a few months after, we know that ChatGPT changed the landscape completely. And we enter in 2023, just after a few months, I can say the year of large language models. And in fact, to the next EGI conference, I show cartoons saying, okay, so we don't know how it works. Maybe, I don't know if we can trust, but I want to adopt it. And I want to adopt it now. And this happened. Many companies already adopted it. In the Gartner report, they say, okay, this is the already adopted. Generative AI is already delivering real value to users. In the same conference, I also noted that there are few open source models, but a few months ago, we have Meta releasing various models from 8 billion to 400 billion of parameters. So it means that to run it, you need 800 gigabytes of memory that are open source, even with a restriction on the license to use it. But let's say from the research community, there's still lack of open source models that are really challenging to train because you need a lot of computing and RAM power. And this could be maybe we don't know, maybe we will see to the next conference, but could be the year of agentic, so of large language model that interacts with other language model and with tools to build, to break the problem and build the final solutions. What if we look ahead instead, we have to define a map, a roadmap for the federation strategy that will include obviously also the part on the AI for the next 4 years. And it could be very difficult because this landscape changes so fast that we don't know what is going to happen. We know that OpenAI released now this new model using reinforcement learning also on inference, so making it heavier also to make inference. It's only a preview, and we will see what's going to happen. But let's look at what is needed. So to the process, the first part is the getting the data. So bigger model require more data, and this data need to be of quality. So we need to collect them, to clean, to preprocessing, and then make them ready to be processed. For this, we can also use what is called the future store, where we can store these features in a standard way, so that can be used for also for others. Maybe we can also make this feature fair, so that can be findable, accessible, interoperable, reusable. And we need a governance. So who can access these features to train their model or to make inference? Then this is the part that is hard from a computational point of view, but also from a particular kind of storage, that is the RAM, that is the part of training the model and fine-tuning it. There are well-known frameworks like PyTorch and TensorFlow, but we have to go in parallel if we want to get the results in a reasonable amount of time. And so there is what is called a distributed training, running this training in parallel on multiple nodes with the multiple GPU. Or there is another option that is federated learning that is used in particular if I don't want to move my data, because maybe I don't want to share, so maybe are sensible data. And so it's still running in parallel, but in distributed way across different data centers, or to the edge, for example. The result then need to be stored in what is called the model storage. So a model registry with all the models. Even here, this probably something that is lacking is making this model fair, findable, accessible, interoperable, reusable. So having also a catalog with this metadata, also that link to the data with which this model has been trained, so that the process can be reproducible, and the governance. So I want to share my model, with a group, with all, and so on. And finally, we can use this model. So we need some inference API. We know there is the OpenAI API, but we can easily create our endpoints to serve our model. We can do it locally or in the data centers, and avoid to share our data with these big companies. And also for this, there are different frameworks available. So this is, let's say, the functional requirement for the process, or what is called, if we automatize this process, is called the MLOps. So, okay, we need there a simplified version. There is observability to see if this model is making the inference is working well, and we can repeat the process, or retraining the model, or adding more data, and so on. But let's say a simplified version of the process. How I think to implement this in the EGI is based on the bottom on a Kubernetes, because we already use it for the notebook. We also have a managed instance of Kubernetes, and we can add, for example, interlink that is developed in the interTwin project to offload the EV part of the process to other resources like HPC or another Kubernetes cluster anyway. And we can use Oscar also to make the inference, so exploiting its function as a service function. On top, I put two frameworks that was already in my first landscape analysis. MLflow, mainly for the storing of the model, even if in these last years, both frameworks are developing new functionalities and are start to competing among them. But I think it's not important in the end, the framework that we are using. We can change them with the time. It's the functionality. What we want to store the model and make available, and decide using our mechanism for authorization to decide if I want to share this model with a group or with everyone. And the same thing we want to do with the serving. We have this API endpoint, but we need to account for their usage and also to control who can access these endpoints. And Kubeflow, so its main point is building pipelines, but there are other frameworks that can be used. And also Kubeflow is now developing the part for serving the model, but also for storing them. It's less mature than MLflow, obviously. And it also has the component that allow you to have Jupyter. So what we have now on top of Kubernetes can be moved on top of Kubeflow for the Jupyter interface. And we have projects that we will see in the next lectures. AI for EOSC, I imagine, that several components, including MLflow, for example. But what I would like to have, since we have a federated infrastructure, to move this flower a little on the bottom, allowing so to make federated learning in the EGI federated infrastructure. How can we go ahead in deploying this architecture? Is through projects that are going to start next year. One is Rescale, and Rescale will go through the flow from data preparation to the serving the models. And so will give us the opportunity to build all these steps, all the frameworks that are used in the steps that we have seen before. And the other one is the EOSC Data Commons, because in the EOSC Data Commons, we are using interactive with large language models and databases to enrich the data, but also to packaging data with tools. And this could be the foundation to have an automatic deployment through natural language interface for the tools. So how can we build? We need, obviously, the participation of all the federation and EGI community. So we will have on top the platforms that goes from AI for EOS to Rorro, so all functionalities that are in some way under development, already have been developed. And we want to make the way that some of them became the foundation also for the future projects. So instead of every project building their own model registering using MLflow, let's try to have an instance of MLflow that can be used by all the projects. And the EGI community, obviously, here can help with the storage and compute, but also with the tools to managing this storage and compute, from the data staging and replication, but also to the deployment of the infrastructure. While the EGI Foundation can help in the federation, in the interoperability standard for the data, but also for the computing, and finally can facilitate the exploitation and the management of the services. It can then be reused by all the EGI science community. And I have to conclude now. So I put here some challenges. There are many, obviously, but I think my message was to try to build something together, not for every project, but that can be shared among the project, so that the project can focus on the effective real work that need to be done. Try also to share GPUs and allocate them more dynamically. These GPU resources are expensive and, let's say, rare, so we need a better model to exploit them, so that can be available to everyone. We have opportunities for use cases already inside the EGI Federation that we can use, for example, natural language processing to improve our documentation, but also to provide the infrastructure. I would like to have an interface where I say, okay, can you deploy me a Kubernetes cluster, open this port without going there and do it how we do now. I think this is going to happen already now. We can use, for example, to identify patterns and predict system threats. So these are use cases that we can already apply in our federation. And yes, I think the trends is the agentic workflow. So the ability of large language models to interact with other tools, with other large language models, or maybe having a big models interact with the small models that are more efficiently and more green. We have also to look at, to try to consume less power to use these tools. And so I think this value that our openness and collaboration can be used to, let's say, let's share the idea and build this new architecture together. So if you agree or not, please contact me after. We don't have time, I think, for questions. And if you want to participate also, let me contact me, because we have to build these strategies in the next few months to be ready for the next 4 years. Thank you.
Thank you very much. I'm Gergely Sipos. I am the coordinator of the Imagine project, which I will present through let's say, a helicopter view covering all the different activities. And then my colleagues from the project will follow up later in this session and the next session concerning technologies, concerning zooming into specific use cases. So I'm trying to give you the overarching view of why we are doing what we are doing and what are the outcomes that you can expect, what are the ways to engage with the project and benefit from the project. So the fundamental problem that Imagine aims to solve is how to make value out of the imaging data or images that are generated in aquatic sciences. And the overall data tsunami in aquatic sciences is evident, but inside that tsunami, there is quite a few waves related to images because the technologies for underwater, overwater, flying cameras is kind of tremendously broadening, giving lots of data. This data is now quite well curated or at least quite well preserved. There are well-established networks, databases, large initiatives, inter-European, inter-global initiatives where the data goes to. But the question is how to make use of the data. What are the scientific questions that we can answer through those data? And for us, the artificial intelligence and the emergence of this whole field gives us new opportunities to use artificial intelligence for the image analysis. And that's the objective of the project, which is achieved through the deployment, validation, and operation of a dedicated AI platform, which is applied for different use cases and portfolio of use cases, scientific questions from aquatic sciences in order to enrich the data and turn the data into online services through which scientists, policymakers, different agencies can interact with images and make use of the images for various kind of scientific policy-making questions. The project started exactly 2 years ago. So we are entering the third year in this month, 4.5 million EC funding with a relatively large consortium about which I'm going to talk in a bit. One important aspect of the project, I think, that I want to highlight is that it's on one hand, a development project. So we are developing new services for image analytics, but we also have the service delivery aspect of the project, which we do through virtual access provisioning funding mechanism from the EC. The consortium itself, which is indicated in the bottom, consists of 24 institutes, which is a mix of expertise, both from the infrastructure communities, data management communities in aquatic sciences, and scientific communities or institutes that want to make use of the data. So it's really a kind of multidisciplinary playground, I would say, that brings together different experts, line them up behind a shared goal of making value out of imaging data. The most important beneficiaries, I would say, for the project are research infrastructures that are operating in this domain. And we would like to demonstrate to them how much more they could make from their data that they are already producing, that they are procuring, producing, archiving, and storing and sharing for the community. So hopefully the project will generate services that can penetrate into the core service portfolios of those research infrastructures and at least give them indications for future projects to strengthen these services, broaden these services in order to embed them into their daily operational pipelines. Let me go to how we achieve that goal. We achieve that by bringing together a dedicated subset of the EGI Cloud Federation for providers operating OpenStack clouds from Spain, Portugal, Turkey, and Ireland. They together contribute storage, CPU, and GPU hours to the project. And on top of that federated infrastructure, our colleagues who are developing a technology in the AI for EOS project, deployed the technology and customized it for aquatic sciences, offering a one-stop shop to implement the whole life cycle of AI, which is a very similar pipeline I'm using here that Marco used in his presentation, which basically starts with bringing data into the models, training the models, validating whether they are accurate enough. If they are, then we can publish the models for inference, which is basically serving the model as applications for other scientists so they can use their own images to kind of play with the model and to get understanding of their images. This upper layer includes the use cases, which here I quote thematic services. So by thematic services, I mean trained models that are turned into online services. We also have kind of lower technology readiness models that are more for validation to indicate new pathways for research infrastructures. And overall, this work happens in what we call a competence center. A competence center is a distributed team that works together across all these expertise areas in order to achieve and implement this cycle. That's probably the only screenshot I use, and Alvaro will talk much more deeply about the AI for EOS technology and how it serves the needs for the users. What I want to say is that this is basically the entry place. I think that's even a public section of the Imagine AI platform where, for example, the already available models can be browsed. And that's the starting point both for users who want to reuse models, but also for other use cases who want to build on top of an existing model and kind of use that as a starting point to train the model for their own purposes. And other views in the platform provides different statistics, for example, and I just feature this because of the reference to the virtual access funding, which requires us to also measure the usage. And that so far in the first 2 years was focusing on measuring the usage of the computing layer and the platform services. And in the third year, we are entering into the level of the thematic trained models. And then we will monitor much more closely on the end user scientific usage of those models. And through that, obviously, we generate the underlying CPU storage and other statistics. But in the first 2 years, this, let's say the hard infrastructure layer was the most important for measurement. Okay, and where we are with the project, as I said, we just finished the first 2 years, basically, and we're entering into the era of these major AI services, plus publishing best practices for image analysis, and another colleague from the project will talk about that. And in the remaining 12 months, basically, our focus is on making these services used, demonstrated, and sustained through different mechanisms, which includes partnership with research infrastructures, follow-up projects. As you will see, some of the use cases have also a kind of commercial exploitation path. So this slide just aims to tell you what are the 3 outcomes we achieved so far out of this work. One are these trained models that are now turned into image analytics services. The second are data sets that we used to basically feed and power and train the models. And we publish those data sets also alongside the models for 2 purposes. One is to increase trust in the trained models, so people or scientists know on which data sets the models have been trained. So in case they are interested in, for example, data biases, then they can look into the original data to see what was the occurrences of certain types of fish. And the second reason for this is that these are already typically labeled images and can serve very well other future model training activities outside the project. So that's in itself is an asset that can power other projects, other initiatives in the future. And the third, which is a new publication, is the good practices document, which captures in a written form what are the lessons we learned and what are our recommendations or tips for future initiatives, other initiatives that run in parallel and want to use AI for image analytics in science. The 5 Major services or use cases are just recently reached the status of delivery, and they are published on the website. So this is the project website, a snapshot of that, and you can request access to the services. There is a Google form embedded there that you fill, and then our colleagues will pick up your request and will guide you on how to use or benefit from the services. On the next slides, I have kind of one slide per each of these 5 major services with the main purpose to indicate you the diversity of scientific questions that we can answer in aquatic sciences with the use of AI and images. Okay. You will also see from this diversity that they are not just always kind of online services that anyone can go to. Sometimes, for example, this first example is a use case or a service that can support cleanup operations typically run by governmental agencies. And it does that by providing you a drone-based image analytics as a service where the colleagues from Austria can go to the site, run the drones for a few days, gather data about the area in order to understand the pollution of an area, typically after floods, especially in Asian territories, and understand what's the scale of pollution and also what are the types of pollutant in the area in order to be able to run more targeted cleanup operations and to prevent similar events to happen by putting out more restricted policies for certain types of factories, certain type of pollutants or activities. So here the input are the drone images gathered by the team, and that breaks down into images that are kind of a subset of the territory, and using a classification, which is also a new kind of system or a new kind of standard in this field, using this classification schema to indicate the level of pollutant in each of these area cells, and also the type of pollutant in that area. The next service is concerned with a system called ZooProcess or ZooScan. That's a microscope basically that can be used for plankton observation. And here the challenge is how to speed up the analytics of those ZooScan images by automating the identification of objects on those images, plus recognizing the type of object. And the big difficulty that the team faced here was that these planktons are overlapping on the images. So it was a huge challenge to even identify the proper border of each of these planktons. You can see here at least, or feel the diversity of shapes and forms that these plankton come from. So this can speed up analytics for those researchers who already have zoo processes, and there are quite a few hundreds of these units globally already embedded into the operations of marine research institutes. So clearly the user of this setup are those institutes that already own the ZooScans or will purchase a ZooScan in the future. The third use case, I don't know, no, it's not a video. I forgot to include the video, but this is basically a live stream coming from an underwater observatory station near the coast of Barcelona, where if it was the video version, then you could see fishes floating around. And this fish identification application basically superimpose the type of fish that it recognizes using different colors to indicate the different species and pointing you the level of accuracy for recognizing the different type of fish. So this is something that the OPSI Underwater Observatory wants to put inside a continuous production pipeline. So instead of just pushing out the raw video stream, they also want to gather statistics on fish occurrences. So for them, the scientific outcome here is not the nicer video. It's basically an Excel sheet that would give you over a certain period of time, the fish occurrences in that region across the different species. And of course, it has also this very nice kind of engagement tool, the live video stream, that can attract attention from the general public into what's going on near Barcelona. And we have different kind of sub units or sub use cases for the same purpose, all coming from the EMSO research infrastructure, which in itself is a federated network of marine observations research institutes all over Europe. We have one from Barcelona dealing with the ecosystem near OPSI. We have a second one from Ireland dealing with, let's say, a similar challenge of counting occurrences of specific animals, but you can already feel from the pictures that the ecosystem as well as the environment is very different here from what we see near Barcelona. The lighting is much dimmer, therefore the whole challenge of recognizing images or recognizing objects on the images is very different. In this particular case, this kind of crab species is what they are interested in. And the third subset here is yet another EMSO site that's in deep water, I think in the Atlantic Ocean, but maybe the shop can be more precise. Azores, yeah, near the Azores. And that's fundamentally is the same challenge to recognize a certain types of fish, but because the ecosystem is different, fundamentally you need to train the model differently with different inputs and use different lighting techniques or cleaning techniques in order to reach the adequate precision. Okay, the next use case will be detailed later by a colleague in a separate presentation, so I'm not going into that, but it's working with satellite images in order to predict the kind of layout of oil spills on the ocean or open seas using wind and water kind of prediction techniques and simulation techniques empowered by AI. And the last use case that was turned into an online model is another kind of microscopy-based recognition system. It's using a technology called FlowCam, which is another type of microscope using another type of imaging technology inside and suited for a different type of species. The objective here is to help researchers enrich a central large image data repository that's populated from different locations using the same technology. And the AI here helps to identify the objects on the images and therefore enrich the metadata for the database. So the database itself becomes more valuable, suiting for analytics, for ecosystem monitoring, and very different types of use cases. And we have also the three less mature use cases. For these, the objective is to reach a demonstration level that we can demonstrate for different stakeholders that would be the consumers. One is an interesting use case, which is using underwater noise as input and turns the sound basically into images using Fourier transformation, because images are easier to work with than sound streams, and tries to identify what is the source of the noise, whether it's human-made construct or illegal fishing boats, or it's a natural element, and if so, of what type of natural element. The second is another interesting, unique one, using CCTV cameras deployed on the top of some hotels on the island of Palma in order to predict a special wave formation that can be dangerous for the beachgoers and can basically suck the swimmers into the open sea and therefore threaten human life. And the third is identification of diatoms in freshwater. So that's the only use case we have for the freshwater ecosystems. All the other are working for sea and ocean ecosystems. So I talked about the use cases, and these are turned into online services and you can request them. And I mentioned that we published the data sets. These are the training data sets that they used for the training. You can access them through the website. If you are interested, you can see here the main characteristics. And the best practices document is available since the 1st of October in Zenodo. That's, I think, a very nicely written document from which you can learn, even if you are not working in marine sciences, but working in AI with images, because there are very helpful tips for each of the stages of that workflow that I used in the previous slides. And let me close off with this opportunity that is basically call for additional use cases. And we are eager to work with additional use cases that can complement our understanding of the problem space for working in marine sciences with images. And we offer both human support and infrastructure support for them to achieve their goals through the imaging AI platform that we offer on top of the federated cloud infrastructure. We already signed up 3 of these external use cases, and they are, again, very different types of problems, but all commonly share images as input. So thank you very much.
Just a quick question, maybe in the meantime, we can switch the presenter. So we will continue with the best practice for supplier of image collection and analysis tools in aquatic science. So still from my imaging project with Elnaz Azmi.
Yes, thanks.
Thank you.
Should I click something or just? So, hi everybody. My name is Elnaz Azmi from Karlsruhe Institute of Technology in Germany. And I'd like to welcome you to my presentation about, again, I imagine you heard, but this time about best practices for suppliers of image collections and analysis tools in aquatic sciences. So it will be a following talk of my colleague here. So I imagine I will talk today about a bit about competence center. You heard already thoroughly and in detail about the competence center, but I will just briefly go through for the newcomers, and I will talk more about best practices that we learned during the whole I imagine project till now, and the lessons that we learned via the experiences of the use cases. So here you see some introduction about competence center, that we have AI and IT experts and also domain experts, which we divided into some work packages. Work package 3, which consists of domain experts, and work package 4, which consists of IT experts with which also provide AI framework for us, and the whole center supports the use cases through monitoring and regular meetings that we have, bi-weekly meetings with our use cases. And we have also 3 annual competence center workshops, which you see here some nice pictures from 2023, which it was in France, and 24 in Mallorca. And we also provide some input for best practices that we learned, and we support standardization and improving the quality of the data sets in marine science. And here you see some overview of the synergies that we have. So here you see that we work in collaboration with AI for EOSC, which they provide the platform and the experts from AI. And also we support with work package 3 with domain experts and AI experts. And you see in another work package, which this is collaboration between these two projects to make the whole, I imagine, available for use cases. And the whole support is being done for the complete development cycle of AI models. And you see here the whole workflow containing, starting actually from data and labeling, and then training your models, and then doing the cycle till you have a desired output from your model. And also it contains the sharing of your model in our repositories, or monitoring your model, and also deploying it to other use cases. So here are some topics that I will go through, and you can also have a look later in our documentation, but it's going through the deep learning models that we used, and also annotation tools and pre-processing techniques that there are need for that, and till doing some data bias reduction, and finally some user experiences that we documented. So, so starting from the whole workload that you see there, from the data, we can't do anything without data. So we need some data and also labels for doing these supervised machine learning methods. And that's why we need also do some annotation. And we went through good annotation tools that you see here. So here are some examples, which CWAT is the most used tool from our use cases. It's user-friendly, it's robust for annotation, it has good features, and it's flexible. Also Label Studio, which it's a bit more complex to use and install, which is one of the experiences of the use cases. And Beagle, for example, is a web-based platform for marine annotation, and RoboFlow, which is cloud-based. So here I just show you some examples, but you should really find the best annotation tool based on the advantages and the disadvantages that we documented to find a suitable tool for you. And you know that raw data has a lot of noise, and they are not clean. And that makes the whole modeling and predictions false, actually, if you use your noisy data. That's why you should start with data cleaning, removing noise and errors, inconsistencies in your data set. So there are some techniques like normalization and standardization, which makes the data more consistent and bringing them into same scale, or handling imbalanced data, which you should do some oversampling or undersampling based on the classes that you have. Data augmentation is one of the methods that most of the use cases use. So doing some transformations, flipping, rotating, making your data set more generic and generalized. So after that, you have your data. You want to do and store your data set. So we give a tip, which is Zenodo is a good platform to upload and publish your data set. And it's open access. It has a robust platform, which you have DOI for your data sets, and you have version controlling. And here you see a QR code that you can just click and go to the website. So the data sets that you have, maybe they contain biases, and that's why you should really do some you should use some tool to improve and reduce the biases in your data set. You see here we offer fair EVA tool as a tip. So maybe you heard yesterday the talk of Fernando. You can just refer to the talk. Maybe the presentations slide are published. This tool helps you to improve the fairness of your published data sets. And you can, it's also in collaboration with Zenodo, and this is a good tool to use for improving the fairness. So, and then when you have your data available, then you want to do some training and testing your model. So we have different deep learning models, but we can, from the use case experiences, we have some tips for classification. For example, they used MobileNet, and for object detection, they use YOLO V8, which is the most commonly used for object detection, and it has a good performance. And for segmentation, again, you can use YOLO V8 and Mask2Former, for example, which has better performance in panoptic segmentation in comparison to Mask RCNN. So you should really have a look to the documentation and see which method is better for your use case. And when you have your model, you want to train and test, and you can try Imagine Marketplace, which you can upload and share your model and then start training with that. So, and you can click the QR code, which is the direct link to the platform. And when you have your model, you just need to test and see if your model is giving the results that you want to. And then you need to evaluate your model. And we have some performance metrics here. You can see that our use cases are mostly used. For example, accuracy, which is the ratio of correct predictions over total predictions, or precision, which is the ratio of correctly predicted positive observation. You can read, it's just for you to, for later. I just listed the whole, like some examples, recall, F1 score, and the mostly used also the metric is intersection over union. This is also very good for image analysis, which you have overlap between the boxes that you have, and then the greater overlap has a higher intersection over union. So then you want to also monitor your model performance, which we tip you with experimental tracking with MLflow, for example, which is a very good, efficient tool for tracking of your machine learning models. And so, for example, maybe you also tried with TensorBoard. It has a bit less functionalities than MLflow, and also it's single user. For MLflow, we have multi-user use cases, and you can just try with more use cases and more users. And also TensorBoard is self-hosted. For weights and biases, so you have this disadvantage that it's by default not appropriate for production environment. And here I refer to the talk of Valentin Kozlov and Lizana Berberi, which you can just get more into the details of MLflow. So finally, you have your model, everything is okay, and you want to serve your model to the users, and you want to share, you want to serve this, and you can use, again, Imagine Marketplace. And you saw also some screenshots in previous presentation. Just click the QR code, you're directly in the website. So the models are published as Docker containers, and then you also can try with this try button for 10 minutes, just without any authentication, and you see how it works. And for deployment of your model, also we advise you to use OSCAR, which is a good, efficient, scalable deployment tool for running your AI inferences. And here I have some reference to the talk of Amanda, which was yesterday. Just have a look on the details of the presentation, maybe. So, yeah. And all of these details and topics are now public from 1st of October, as you already heard. Just click. It's the DOI, and yeah, you have everything there. Just try it. And here I have also some links to our marketplace, to Imagine platform and Zenodo, which you can have a look later. So thank you for your attention, and yeah, I'm here to answer the questions.
Any questions?
Thanks a lot. That was informative, even for me. About the Fair Eva tool, I looked it up. According to their website, it's designed for sound data. So how is that used for images?
So it's about the model. So you have you have your repository, you have your data set, and then they have this tool to just check how your if your data set is publicly available, it's reproducible, and yeah, it's just
maybe I checked something else. but that there is a Fair Eva, which is for bias detection.
Really? No, there's a website for Imagine.
Cool.
Yeah.
Okay.
Also, if you click,
so be careful.
Yeah, yeah. I mean, I have a link there. If you maybe later just cool. Check.
Okay.
Yeah.
All right. Okay. Because you mentioned it's used for bias. But
yes,
there is another tool called Fair Eva for biases. Just be careful.
Maybe just similar name. Yeah.
Other questions?
Yeah, if you find some questions, you can ask. I'm here today. So yeah, thank you.
Thank you. Now we have another, I guess, use cases from Imagine. Bayesian optimization workflow for improving oil spill numerical simulation. Mariano De Carlo from CMCC, right?
Yes. Okay. Good morning. I am Marco De Carlo, and I am a postdegree researcher from the Advanced Scientific Computing Division of CMCC. And today I'm here to talk about Bayesian optimization workflow for improving oil spill numerical simulations. The problem of pollution caused by oil spill is still one of the most damaging environmental disasters for marine ecology and for human health. For this reason, when an oil spill occurs at the sea, we must be able to predict in advance the location and the trajectory of the leak in order to effectively and efficiently organize emergency response to limit environmental and economical damages. So current oil spill models like MEDSLIC2 rely on a significant amount of simulation parameters to be calibrated. These parameters are case-specific parameters for each configuration and are end-calibrated parameters that may lead to subjective bias because we rely on the scientist's expertise. The procedure is a time-consuming procedure based on a trial and error, and the risk is to get out to compromise the performance of the simulation due to inadequate choice of parameters. So our goal with Bayesian optimization is to create an informed approach for parameter selection based on some optimality criteria. The calibration must be automatic to save valuable time and resources, and thus ensure an effective results in the shortest possible time. To improve the accuracy of simulation, the idea could be to assimilate available satellite data, all while still maintaining the physical consistency that characterizes the approach. In particular, the Bayesian optimization identified new optimal setting, raising question about parameters' influence on results. This approach remains physical consistent as parameters are sampled within their physical ranges. So what we want to do? We have a black box function, an expensive black box function, which can be an experiment. For example, an experiment expensive in man-hours. Schematically, our approach is like this. Practically, we query this black box in order to get out results, noisy results. And from this data, we build our machine learning model, which is our surrogate built with the Bayesian strategy. Then we requery this machine learning model to get the best possible parameters, which we put back into the black box to evaluate it cyclically. So how does BayesOpt work? As you can see in the figure, for example, you see in red a very simple one-dimensional function, a smooth function, that we want to optimize. The dotted line represents the mean, and at the top and the bottom, you can see the standard deviation. So where the function is conditional, the standard deviation drops to 0. Then you use your surrogate in the form of mean and standard deviation to construct what is called acquisition function. This is the second part of the Bayesian strategy. There are many forms of acquisition function, for example, likelihood improvement function or expected improvement function. And what is their purpose? Their purpose is to give you another set of points on which to query your black box function. For example, here we can see the expected improvement function. So we query this function, we find a maximum, and constrain our objective function f on this point. So as you can see, it progresses, it goes there, find another maximum, and constraint on it, and so on until the convergence. So what we are doing with our approach? Our proposed architecture integrates the numerical model MEDSLIC2 into the Bayesian optimization workflow. The first step is the MEDSLIC2 configuration. MEDSLIC2 have two configuration files, one for configure the simulation and one for the simulation parameters. The first one is still the same during all the workflow, but the second one changed through the Bayesian optimization. The second step is the run of MEDSLIC, who give us the results. These results is evaluated by a metric named FSS, fraction skill score, who is a metric similar to the overlay. But FSS evaluates also the false negative point. The third step is the maximization step. Now the Bayesian optimization try to find a new point on our objective function and try to maximize the FSS metric. After that, the Bayesian optimization find sample new parameters, such as wind drag and horizontal diffusivity, for example, and then substitute it into the config2 file. So at the end of the process, the new values found are replaced in the configuration file by restarting the process. The number of iterations of the process can be chosen by the modeler depending on the time and the computational power available. It is clear that better values will be more likely to be found with a larger number of iterations, but excellent results are also expected with only a few iterations of the entire workflow. This investigation was carried out in the context of the imaging project. And the main goal of this project is to provide a portfolio of image datasets and advanced artificial intelligence-based analysis tools applied to aquatic science. Our scientific use case as CMCC focused on the oil spill detection through data-driven approach in collaboration with the University of Trento and Orbitalos. And our contribution as CMCC includes enhancing the current monitoring and forecasting system by establishing an operational service on the imaging platform through the architecture described above. So this is the result. In this slide, you can see the experiment on the Benias oil spill event occurred in Syria, in the Benias, in the August of 2021. The satellite observation are reported in blue. The MEDSLIC2 simulation are reported in red, and whereas the overlay between the two is reported in green for 3 consecutive days. As you can see, the simulation had a significant improvement using the optimal parameters found by the Bayesian optimization approach, and in particular, we had a really relevant improvement with almost a 20% of extra overlay. So substantially, we improved the simulation performed with the default parameters in a significantly reduced times without the help of the scientists' expertise. So thank you, and thank you to the Imaging Project for supporting us in this research.
A couple of minutes for question.
I have one. Have you tried or considered to use a pure deep learning approach to model the oil spill by using a multimodal approach, like including satellite images, atmospheric data, oceanic data, and see how it works? Or maybe there are not so many oil spill events that you can rely on to get the data, but yeah.
Yes, we think about an artificial intelligence or a deep learning algorithm, a classical deep learning algorithm, but we hadn't announced the data because oil spill is a very rare event, and depending on the zone. So for Syria, for example, we have 7 or 8 images, only these. For the other event, we have 1, 2, or almost 3 images, and it's depending on the zone. So it there is a very big variation from zone to zone. So this is a problem for a deep learning algorithm.
Yeah, because the satellite has to pass, the event has to happen, and
Yeah.
no clouds. Okay.
Yeah.
Can we then go to the next speaker? That is Estibaliz Parcero. The process bridging cloud and HPC for scalable event-driven processing of AI workloads. And I think the project is interTwin now,
Exactly.
right?
Yes, correct.
So we are switching project now.
not my presentation. Okay. Okay, yes. So thank you again. My name is Estibaliz Parcero from the Universidad Politécnica of Valencia, and I'm here to present this integration that we did inside the interTwin project. It's bridging cloud and HPC for scalable event-driven processing of AI workloads. And let me split, I'm sorry, but the colors are not showing well, but it's okay. I split the title into three. Bridging cloud and HPC is what we want to achieve. The scalable event-driven processing is how we run workloads. And here I'm going to talk mostly about OSCAR that was already mentioned in the previous talks. Is the open source serverless platform developed in the UPV. And also I'm going to talk about AI workloads a little bit, and this is why we need that bridge. And well, this is the index of the presentation, and let me start with the AI workloads. The thing is that there are more and more ML tools available for cloud. So AI engineers are used to use them because of the benefits they offer. They are accessible, scalable, flexible, efficient, and interoperable, for example. And most of the time, these cloud native tools provide necessary compute. However, there has been an increase in the number of parameters for machine learning models, for example, and training tasks takes a lot of resources, but also inference tasks with this kind of models like large language models, diffusion models, or GANs. Luckily, yes, the computation capacity is also increasing at the same rate, but most of the time, those resources are only available on HPC clusters. So how to bring together those two worlds and be able to benefit from cloud tools and HPC resources? It seems like bridging cloud and HPC is a good idea. But I'm not the one saying that. There is a lot of scientific literature that are looking into that. And for example, this paper from Hefla highlights the importance for climate research and machine learning in general. We extracted some key ideas from this paper. The need to leverage containers, the need to improve communication between cloud and HPC, and also enable access to data. I'm going to talk now about the OSCAR platform a little bit. As I said, it's an open source platform for serverless event-driven computing. It's a cloud-native tool, so all the benefits that I talked before also apply to this tool. This is a general schema of the architecture. I'm going to mention some of the advantages of using OSCAR. It has, for example, multi-cloud support, can be deployed on on-premises, public, and federated clouds. Can be easily deployed using, for example, the infrastructure manager that is in the EGI catalog, and it's very easy to use. It also offers flexible interfaces. You can access OSCAR from a web interface, an API, or a command line interface. Here I saw some examples. It supports multiple storage backends like Minio, Amazon S3, OneData, and also any storage that uses the WebDAV protocol, because we developed this tool called DC-Neos data connector through Apache 9V for OSCAR that connects this kind of storage providers to the OSCAR services.
It's a command line tool, so it's very easy to use to be able to configure these data flows. I will talk a little bit more later. And also, EOSC has this component called fast supervisors. It's the COP component, and it's the middleware between data providers and OSCAR services. I'll say later why this is important. Another benefit of OSCAR is that the services are container-based, so the user can customize the runtime environment. For example, in this case, a user can pack TensorFlow with her model and the dependencies and a script to run the OSCAR service, all of in a container. And OSCAR is event-driven processing, has event-driven processing. So when the user uploads data to the storage, that will generate an event and it's going to trigger automatically an OSCAR service that has been deployed. This OSCAR service will create a pod because OSCAR is on top of a Kubernetes cluster. It will be nice if this pod it could be also executed in a HPC environment, for example, to leverage their resources. And that's where Interlink shows up in this integration. Interlink is a tool developed in the INFN, and it is composed by two parts. One is the part that is installed inside a Kubernetes cluster. It's a virtual node that Interlink is watching for jobs that are incoming. And the other part is an API that is in the remote host that can be, for example, an HPC cluster, and is where the job is going to be offloaded. And this is general schema of how this is working. And I'm going to, well, yes, just some technical aspects. I'm not going to go into detail. Just we had to perform some changes in OSCAR in order to integrate it with Interlink. But all of these changes are transparent to the user. So the use case, in order to try this integration, we use this the use case provided by CERN, also inside the interTwin project. It's an AI pipeline that is using the tool iTwin AI, also developed inside the interTwin project. And this AI pipeline is configured to run an inference of a 3D gun. That is a model pre-trained to simulate particles in the high luminosity Large Hadron Collider. And also we use a distributed storage system called Dcache that is developed in DESI, also inside of the project. Well, here is the general workflow all of this process. I'm going to go step by step, so you can see how easily it's for the user. First of all, the user will create this container with her application and can create an OSCAR service over there, for example, using the web interface. Next step would be, in this case, like I said, we are using the cache, so we need to establish a data flow that is going to connect these events generated by the cache to OSCAR. So the user can use these scenarios to create this data flow. And then Apache NiFi is going to monitor these storage events. When the user uploads the new data to this cache, then the cache is going to generate that event, and it's going to be stored in Apache NiFi in a queue. We can also, as users, customize the rate that we are going to ingest those events into OSCAR. And we are doing that by using an HTTP request. And when OSCAR receives that new event, it creates a new OSCAR job. And this job is going to be placed inside the virtual node that I mentioned earlier, that is be watched by Interlink. And this job contains the event that with all of the user credentials and all, and also this file supervisor that is the OSCAR component that is going to connect data with services. So this job is offloaded by Interlink into, in this case, an HPC cluster. We use the HPC Vega in the Izum, Slovenia. And it's created a job. I mean, a job is created inside the HPC that first of all downloads the data from the cache. Then this data can be processed using the container that the user specified. And again, the OSCAR supervisor will upload the result to the cache again. So it's available for the user. This is like a possible simulation of these particles that, well, it's a Dolly generated image. So the user can examine the data. As I said, this service is already created in OSCAR. So the user can upload the new data again and again, and it will retrieve new results. Coming back to the key ideas that I mentioned earlier, I would like to see if we could make some connections. So we did employ containers to be able to run the workload, both cloud and HPC. For communication, we use Interlink that establishes a communication between cloud and HPC. And for the access to data, we employ this component, this OSCAR component called File Supervisor. These are some of the experimentation that we performed to see if it's working or not. We used 3 separate scenarios. We had one that is a Kubernetes cluster without GPUs, or this is called cloud CPU. And another 2 inside a HPC cluster, one with CPUs and one with GPUs. In general, we saw that the inference ran 30% faster in HPC than in cloud. And using GPUs is this speed up is going to, it executes 80% faster. So yeah, it seems like it's a good idea to use HPC resources in this case. So as conclusion and in summary, we see that the proposed system demonstrates the potential for offloading compute-intensive tasks to an HPC supercomputer, marking a significant step forward in bridging cloud and HPC, but of course, we are just scratching the surface. And before I finish, I would like to tell you that if you, for example, are developing a use case and see that maybe OSCAR is a good idea for you, if you can containerize your application, and if you can think that serverless is a good paradigm for you, or if you have a tool that maybe could be integrated with OSCAR, please let us know. We are always eager to know about new ideas. As I said, this is closing the interTwin project. So thank you to that project and to these other 2 projects that come from the Spanish government and the European Union. Thank you so much for your attention.
We have time for a very quick question while we switch to the next presentation.
Well, thank you for the interesting talk. How does interTwin declare properties of the job on the HPC? Like how much memory it needs, what's the roll time and stuff like that?
Yes, we use annotations for that. So that annotations are translated into the Slurm properties. I don't know much about that. Maybe if you catch the Diego over there, maybe he can explain you a little bit more about interlink. But yes, what we did was putting this on annotation in the pod. So interlink can export that information to the HPC cluster. Thank you.
The next speaker is Emanuele Donno. I think still a use case from interTwin, ML for digital twin component for wildfire danger analysis via global burned areas prediction and climate projection data.
Okay, good morning, everyone. My name is Emanuele Donno. I'm a postdegree researcher at CMCC. I'm part of the ASC division, the Advanced Scientific Computing division. And today I want to show the ML component developed under interTwin project. It's a digital twin component for wildfire danger analysis via global burned areas prediction on climate projection data. Before starting talking about the component, I want to give you some context about the component itself and about wildfires and their importance on ecosystem and how climate change is impacting on their dynamics and behavior. First of all, wildfires play a crucial role in maintaining and shaping ecosystems. Historically, they've helped maintain long-term carbon neutrality, contributing to the natural balance of carbon in the environment. However, due to the climate change, their dynamics is changing, leading to more frequent and severe events, impacting on carbon sinks like regions with evergreen forests, reducing their ability to absorb carbon. And dealing with wildfires presents even several challenges that must be tackled, such as data scarcity, because extreme wildfire events are rare, and this results in limited historical data. On the other side, we have even complex dynamics, because the interaction between various atmospheric, environmental, and socioeconomic factors make wildfire detection and forecasting difficult, especially on a global scale. Regarding, now we can dive into interTwin project and ML component. First of all, I want to resume about the interTwin project. That its main goal is to design and build digital twin engine capable to integrate with application-specific digital twins. At CMCC, we are contributing to this effort, developing two different digital twins. One on wildfire danger, so it's the ML component, ML digital twin, and the other one is for detecting tropical cyclones. Today, I want to show you ML so we can go on. This component leverages deep neural networks to provide predictions of wildfire danger and help us understand the potential wildfire patterns in the context of climate change. Obviously, the interTwin project, the interTwin digital twin, will support the integration of heterogeneous climate and weather data from multiple sources via data lake. Will enable transparent access to federated computer infrastructures like high-performance computing and cloud. And we provide a complete platform joining general scientific data analytics and machine learning with the thematic software modules for climate data management. And finally, we'll support complex data processing and machine learning workflows, as well as track model and data provenance. Now, ML is this component, digital twin is composed by several Python modules with the aim to support processing and analysis of wildfire-related data. In particular, is composed by 3 different pipelines: data, inference, data training, and inference pipelines. At the current status, ML is able to load and process data and to train, validate, and test the trained model, the chosen training model. Here we choose to, in order to deal with the wildfires, we choose the Unit++ architecture. Moreover, a model's performance evaluation pipeline is currently being developed, and we are evaluating even additional machine learning model architectures for improved results. On the first stage, we have the typical data pipeline in which we load our data set, then we subset choosing drivers and target variables, and then we split it in training, validation, and data subsets. After about the ceasefire cube, the dataset we use, we choose the ceasefire cube. It's a dataset built for wildfire season, for wildfire, and for a seasonal for seasonal purposes. It contains 59 atmospheric and climate and socioeconomic variables on a temporal extent of 21 years, from 2001 to 2021, and with a spatial resolution of 1/4 degree. After we load the dataset, in order to have valuable scientific results, we have to aggregate from 1/4 degree to 1 degree. After that we process the data, and we are ready for the training phase. During the training phase, we load the architectural models, and then we load the machine learning model, and we built it with loading from TOM configuration files, its arguments, the losses, so the loss that we want to evaluate in our training process, even the metrics. Then the complete machine learning model with the optimizer and the scheduler are passed as arguments to a fabric trainer object. And the fabric with the training and the validation data loader, we start the training process. After that, we have the training model that the training model, and its weights are stored. Even the configuration, all the hyperparameters, all the configuration of the trainer, of the fabric trainer, and the model itself is are stored in TOM configuration files in order to can reproduce all the experiments. Finally, we have the inference pipeline, which we load the stored weights, and with the test data loader, we produce these burned areas maps that we save in order to analyze, to have further analysis and reporting in order to provide valuable insights into potential wildfire danger. About the results, as you can see, we here have 2 histograms. One is the matrix about true positives, false negatives, false positives, true negatives, and the other one are all the metrics. So precision, recall, F1, F2 scores, and the Matthews correlation coefficient. As you can see, the AgriCall indicates a strong ability of the model to detect actual burnt areas. And this is reflected in the low false negative rate, suggesting that the model rarely fails to detect an actual fire. Moreover, the aggregate code computed across the test days indicates that, that the model has a strong generalization capability and is consistent over time. On the other side, we have a low precision and an high false positive rate that point out that not only about 1/5 of the areas reported as burnt actually are, but also that the model often misclassifies healthy areas as burnt. This is due to the fact that the task itself is unbalanced. Then, in order to have a vision of the overall model balance, we have to look at F1 score and F2 scores. F1 and F2 scores. Their values tell us that although the model is good at detecting fires, its overall effectiveness is limited by inaccurate positive predictions due to low precision and high false positive rate. Finally, we have the Matthews correlation coefficient. It's about 32.39%. And this indicates the positive but moderate correlation between model predictions and actual data, suggesting the need for improvement. In conclusion, while the model excels at detecting actual fires, ensuring most wildfires are captured, it faces significant challenges in distinguishing between true and false positives. The real versus predicted data comparison shows the model's potential, but also highlights areas for improvement, particularly in reducing false alarms to enhance overall precision. In the future steps for ML for fires, we will integrate ML for fire with the iTwin AI from CERN to further automate the training process. We'll also add the provenance tracking capabilities to ensure every step of the model, every step of the model's training is traceable and transparent. Our next big challenge is validating predictions using CMCC data and SSP scenarios, while experimenting with new deep neural networks architectures to push performance even further. To make ML for fires more user-friendly, we are working even on interactive Jupyter notebooks and GUIs. So, thanks.
We can use the break for the questions. And the session will continue at 11, so after the break. The AI for EOSC, another presentation, so please come back in time.
Please, the people from the imaging project can remain in the room for a moment. Thanks.
So it sounds very similar.
How many persons here? Five. Yeah, it's little and it's covered. We need something where we can take a full photo of people's timing. Okay, okay. That's the important part. So it should be visible when they are having the for the last session. Well, I don't have the something like that one. Yeah, okay. Because this is for official picture. Yes. Because there are new settings. Okay, as long as they are nice, they are not. No, without. Yes, but we only need to. Come questo. Like this one. No, sì, per ritrovare vediamo. So starting from 2 p.m. and yeah, I guess we kind of know it, right? Just what I'm sure that. Ci può stare, right. Oh, yeah, here.
we did in Deep and that we are expanding in AI for EOSC to deliver this AI-based platform for imaging in oceans and aquatic sciences, and EGI for EOSC, where we are enhancing the platform. What is the project? What are we developing? We are providing a user-friendly workbench and toolbox to develop and run and share AI models integrated with the EOS ecosystem. We are building a platform, which is the EGI for EOS platform. We are customizing it sometimes for other projects, and we are building a software stack that we are called AI for OS that powers it. We are not focusing directly on developing AI algorithms. We rely on that for different communities and other projects like Imagine, but we are focusing on helping researchers to build the AI models and transforming them into services. How we exploit already existing infrastructures like the EGI Federated Cloud, but not only, and we are making steps toward providing more fair models, more robust models, and more trustworthy AI models, applying also some state-of-the-art techniques like federated learning beyond privacy scenarios, as Judith mentioned yesterday in her talk, by providing a comprehensive set of tools that allow you to implement MLOps practices in production, like diff detection, and providing users with very rich model provenance metadata covering the whole machine learning lifecycle. See, this figure has been repeated a couple of times. It's very simple machine learning lifecycle where you start from some data that may have been labeled or not. You may have a model that you want to apply to that data. In that case, you create or update your model to be able to process the data, or you can create a model from scratch. Then you repeat this cycle where you train and test the model, then you validate it, and you repeat this cycle until the accuracy is enough. Is okay for you. When you close this cycle, you can share the model back, and from this repository you can serve it and obviously monitor it. In EGI for EOS, we are covering all the steps from having a repository to create the model, to evaluate it, to serve, and to monitor it. And since an image is worth 1,000 words, I'm going to put you here a small video. We can start from a user that wants to develop a model. We have a marketplace. This is YOLO version 8. A user can get a code space inside it. They can put simply a name, obviously a password, no rocket science here. They can request the number of GPUs that they want to use. And here comes the interesting part. They can link with a given storage service that is available in the EOS. They can request a dataset to be downloaded directly from Zenodo or from any given DOI, because the backend will take care of it. Then this is added to the deployment. This is created and launched. It can take some time. The platform is under the hood doing all the heavy lifting. And once the model is running, you can access it here. The colors and the beamer is not that good, but I think that can be perceived. You will get a familiar environment for a data scientist, which is Jupyter Lab. We also provide Visual Studio Code where you can enter. Obviously, this loads. You can check if you have a GPU. In this case, an NVIDIA B100 is directly available for the user. Obviously, the data has been also downloaded and synchronized from Zenodo into the space, as you can see here. Here we have Tesla B100. Here we have the Zenodo dataset already served. And what is also more interesting, we have the model code directly available for the user to start working with it. And what we also provide is users a way to transition from this, which is just launching a development environment in the cloud in a distributed manner, with this other one, which is once you build the model and you contribute it back to the catalog, you can start doing inference with it. I'm going to show you here a very simple example, which is a try me endpoint that we provide for any user, where you can
create a graphical user interface for free. This user interface has not been developed by the user. It is automatically created by the platform, where the platform, again, is doing the heavy lifting, is creating the environment, launching the user interface, and you have, this is, the network here is a bit crappy because I recorded the video here. You can upload an image and you can get your result right away. So this is extremely useful to check if your model is suitable for your purposes before I start working on it. Okay, so now we can submit the image, and here you will see some fishes that are classified with the very same example that Gergely shown beforehand. So that model can be used to produce videos, but this model can also be used to produce images. We can upload another image, and then the inference will take place again, as you can see. So we can provide end-to-end solutions from data ingestion, developing, and serving the models, all within the same platform. So let me go to the next slide. How are we doing that? We are doing that, first of all, taking into account mobilizing different resource providers across Europe. For the EGI Federated platform that are in this purple or reddish cloud, we have currently 3 different providers: the CSIC Scientific Cloud, ISAS in Slovakia, and CNAF in Italy, as you can see here. But we are also collaborating with Imagine, and Imagine has deployed this distributed Imagine platform with sites in Ireland, Slovakia, Turkey, Spain, and Portugal, INCD, CSIC, Walton, and Tubitak. We have built a federated infrastructure on top of an already federated infrastructure, which is the EGI Federated Cloud. And the important thing is that this is completely transparent for the user. The user submits a job to the platform, and this can run in either of these sites. And one important thing is that we are not imposing special libraries or hard requirements for the user. We are not opinionated on that. We provide users with the environment they are used to work with, Jupyter Lab environments, Visual Studio Code, and we are not imposing external libraries to be able to exploit the platform. Under the hood, this is our high-level architecture. This is completely open, following the C4 diagrams that you can see here, but this is a more nice-looking picture. So we start from right from the lowest level, where we have the well-known products like the Infrastructure Manager and the Indigo Pass Orchestrator that we use to provision resources where we build the rest of the platform. The rest of the platform is based on HashiCorp Nomad. It seems that we are the only ones that are not relying on Kubernetes, by the way, but we are very happy with this platform that we have developed using this Nomad, much more simple solution that Saul will show on. On top of this, we run our AI modules, the federated learning server, and the development environments that we offer to the user. And aside, we have the AI as a service and composite AI that was demonstrated by Amanda yesterday based on Oscar. And we also have the MLOps tools like MLflow for model tracking or Rorro for drift detection that we are integrating all together with our rich provenance metadata system that gathers information of every single step of a model in the platform in order to be able to provide this metadata through the dashboard and being integrated with the repositories where we deploy the models like Zenodo, with this very comprehensive metadata of where the model comes from, which dataset has been used for training, what has been the resources and infrastructure the model has used. This is not a lonely journey. We, as Gergely already said, have a very close collaboration with Imagine, but not only. We have started collaborating also with AI for Life, which is a sister project of Imagine, in order to explore the interoperability. And we have deployed a customized platform from them. And we're also collaborating with the rest of the EOSC ecosystem in different aspects. On the technical one, for example, we'll raise to be able to access raise synthetic data from the EGI Federated platform, with Siesta exploiting federated learning capabilities to exploit sensitive data, and with skills for EOS on the fair for machine learning artificial intelligence definition, or fair course for EOS to exploit their services and registries for metadata and crosswalks. We also have collaborations with outside the infra EOS realm, most notably with Flower, where we have made code contributions to the federated learning framework, or with NVIDIA and MLflow, where we are working on model compatibility, and obviously with the EOS DIH that we have used in order to promote the platform towards small companies and innovators. Regarding features, we are here right now. The greenish one are features that are more focused towards the users. The black ones are features that are more focused towards resource providers. So regarding the users, we provide federated learning tools as demonstrated by Judith yesterday. This is the development environment that you have seen, data science templates that will be demonstrated today. We have fine-grained platform usage reports so that the users can be aware of what they are consuming. We are working now on including here also energy consumption and environmental impact. We have integrated the platform with Zenodo, meaning that we automatically deposit models in Zenodo whenever a new version is done, and we are able to automatically gather data sets from Zenodo. For example, those that are deposited in Imagine can be automatically synced and consumed through the platform. We're integrating with external storage systems like Nextcloud, OwnCloud, Google Drive, Amazon S3, and so on. This is already implemented. And we are now working, finalizing the full automation of the resource provisioning via the pass orchestrator and infrastructure manager, and delivering additional tools like online annotation, CBAT, polishing the MLOps pipelines and drift detection, towards the end of the project, where we just streamline the deployment of models as services and make some more improvements. We have a lot of documentation. We have started recording short tutorials with between 1 to 2 minute videos with very specific functionalities as the one that you have seen. These are the QR codes. Well, I don't want to enter into details. There is a lot of stuff here for training and learning what we are doing. And I will close with my last 2 slides. First one is our impacts. We are contributing horizontal services for building AI models in a generic way, but also thematic services for the EOS exchange. AI for EOS is a generic one. 2 examples are Imagine or AI for Life that are very thematic. We have integrated with other EOS and open science repositories like Zenodo, as I said, but not only, also with the EU Open Data Portal, being able to consume data sets from it. I think it was yesterday or the other day that there was this talk about the highly valuable data sets in the EU Open Data Portal. We try to transform how the development of AI models is done for science in the EOS. Why? Because if you develop an AI model for science in the EOS, you should have some robustness and your model should be trustworthy. We're providing tools that will allow to make their models more fair, more robust, and more trustworthy by providing MLOps, monitoring drift with drift detection with scientific and mathematical background. We aim to foster the federated collaboration that I think is extremely important in the EGI Federated Cloud, in the EOS Federation. We think that we should foster this federated approach to build models and not going to centralize these approaches like for building these LLMs. We are contributing to best practices for developing AI models, taking all of this into account. And as I said, I would like to make this emphasis on building robust AI systems that can be trusted. Last but not least, what we have been doing, we are empowering scientific research by providing users with advanced tools focused on AI, like model retraining, federated learning, parallel training in multiple GPUs, both with data parallelism and model parallelism with Rorro and MPI, model monitoring through MLOps techniques, and drift detection. We have implemented the state-of-the-art library for drift detection that is more comprehensive in terms of drift detection techniques, model inference and service delivery. We provide try me endpoints. We provide dedicated endpoints in cloud resources via the infrastructure manager. We provide serverless inference via Oscar, and we provide dedicated inference for prototyping in the Nomad cluster. We provide an IDE for developing based on familiar tools like Jupyter Lab and Visual Studio Code. We provide seamless access to different computational resources distributed across Europe. And as I said, we can help you in deploying the models in production depending on your needs. That's all. Thank you for your attention, and I will be happy to answer any questions you may have, if any. Oh, it's even outside.
Time for a quick questions.
Alvaro, I have a question about the data ingestion part, which you have demoed, and I think it's really nice to see this integration with Zenodo and also the open data portal. Is there a plan about integrating other data resources, and what is your approach when you have specific use cases which will require specific repositories, how flexible the platform is to integrate with all of those? Thanks.
Well, now this depends on the tool we are using. Right now we can get data from Hugging Face, Zenodo, GitHub, by DOI, and several other. I don't remember the platform, but Fixer, DataSite, and so on. But the good thing is that we do not only rely on this tool. Our platform architecture, as we have conceived it, makes a lot of use of sidecar tasks that are running before the user workload is executed or in parallel. Therefore, for us, it is extremely simple to configure another data source and create a sidecar task that is transparently from the user and just add that functionality in the API. For example, in AI for Life, they have, I don't remember the name, but they have their own storage service with their own API. And for that, we need to develop, in cooperation with them, a specific connector to gather that data. But once the connector is developed, plugging into the platform is, I would not say trivial, but it's a very easy task for us because we exploit these sidecar tasks. Therefore, we can just switch the task on the API request completely transparent for the user. Because I think that, I mean, one of the points that I think that is missing is that there are many resources, many repositories in the EOSC, many things that are there, but we need to start putting all the pieces together. Because, okay, if a user has data uploaded to Zenodo, for example, in Imagine, we're producing a lot of data. But if now another user wants to reuse that data within the platform, from our point of view, it is weird that we say, okay, go manually, download it, put it in the directory. And therefore, I think that we need to, for us, it is of paramount importance to start pushing this integration so that all the pieces are connected automatically or mostly automatically without telling the user, okay, you have to go to Zenodo, get the data set and download it. Because we have APIs, we can discover data and we can download that data. Obviously, things are not perfect and sometimes maybe you cannot integrate with a given repository, but I think that this is the way to go, to start putting everything together to make things easier for the users.
Thanks for the comprehensive answer.
Thank you, Tiziana.
I have a question about the development of the models. If I am a user, I have my own model. Am I constrained to some specific framework, or can I bring my, for example, if I developed something with our tools?
We provide you with both options. We have a predefined, not predefined, but it's a growing set of models that the users are contributing back to the platform, or you can start something from scratch, bring your own model and just code or fine tune it in the platform. Next step is to make this marketplace even bigger by providing interoperability with existing marketplaces. PyTorch Hub, Hugging Face, and so on, so that you can even bring the code here and your code will be available for you to develop. Or you can just get a plain environment where you can upload your code, use Git, GitHub, whatever, and start coding. It's not imposed, the framework that you use. It's not even imposed to use Python. You can use whatever you want.
Thank you.
Thank you.
Alvaro. Next we have Valentin Kozlov. We'll continue this journey on AI for EOSC. Okay. Is this one machine learning operations? No, 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 no. We don't have your slide, Valentin, sorry. They are in Indico. Any other question for Alvaro?
So in Germany we have the situation right now that we are building something which is a slice of what you are providing. So what we have to do is we are provided with models, complete models, and we have to give people the ability to use those models in the inference. So how much of this can we use? Because we are just starting. Yeah? So we would build all this by ourselves. Can we take the system? Can we take the infrastructure? Can we take the code? Yeah. And can we try it out?
Yeah, I mean, everything obviously is open, but for inference, I think that if I have not entered into too many details on that, but for example, we are providing 4 different paths because every user has actually 5 different paths. One is not yet shown because it depends in what you want to do. If you want to process historical data, you can use, for example, OSCAR via all this event-driven approach, where you just upload your data, OSCAR does the heavy lifting, and it will process all the information in the background, and you will get the results eventually after 1 day, 2 days, or 1 hour, 2 hours, depends on the amount of data. Then, for example, we have developed these try-me endpoints that are very short-lived, but this is just for testing the functionality. Obviously, you have a model. You say, oh, this model is classifying a litter, for example, the litter drones. And I have the same kind of images. Will it work? Maybe you can just test it. Oh, it works. Then I can start prototyping on top of it. I can do a transfer learning or whatever. Then we have a further thing that is that you can deploy the model in a full-fledged virtual machine that you control on your cloud via the infrastructure manager, where you will get the Docker container, you will get the API, you will get the GUI, and you can do that with a proper node. And then the third one is that for prototyping, we're also providing this deployment inside the platform. So this is managed. This is on top of Nomad, and this is managed. You will get an endpoint. It is protected. You will get the GUI. So it depends on what inference means, because there are different kinds of inference. For example, for real-time video processing, we are under the hood doing that the heavy lifting with a Kafka in order that the people is able to ingest and stream. Then the stream is processed, the inference is done, and then the stream is sent to the outside world, to YouTube or whatever. So it depends on what inference means. There are different flavors that you can pick for. But this is not real time. For example, for that, I think that OSCAR would be the one of the best candidates, because it is able to process hundreds and thousands of images asynchronously, and it will
start processing and giving the data.
Hi everyone, I'm Valentin Kozlov and we continue with AI for EOSC. And now we kind of go a bit deeper into what machine learning operations are MLOps practices, which we first kind of evaluated from a global landscape and then to the practice in AI for EOSC. You probably have seen already some slides, but kind of we change the angle. First, I start with what we understand or what is machine learning operations or MLOps is rather new field, and then there can be different definitions a bit or slightly different. And then what we understand under MLOps, then we did assessment of different platforms and tools. And finally, how we implement these practices now in the project. If you go to Wikipedia and what you often hear that MLOps is about how to deploy and maintain machine learning models in production. However, well, it's also paradigm, it's also a culture and practice. And Google already mentions that this is also about development of machine learning systems. And that is pretty much what I think now is understood more under MLOps, also like Databricks. These are the processes for automation to manage the data, code, models, and operations and monitoring of machine learning models in production. So it's not only to look into the model, how it behaves in the production, but it starts already from the data. And this is about automation. What practices you can apply, what processes you can use, and so on. So then one may say this is about automation of the machine learning development cycle with, of course, the model in production and monitoring the model in production. Then, since we also talk about automation, there can be different levels of automation. And again, this is now how Google split it, these different levels. In a nutshell, level 0, everything is done manually. You start as a normal scientist, you do data validation, preparation, model training, and everything, validation testing, and then you put it somewhere in the model registry and manually deploy it if you have an inference service. At the level 1, you already start automating certain parts. And here, one of the key points is that you start monitoring your model, which is running in the inference service, and then may trigger the so-called continuous machine learning pipeline, or what is also introduced here is continuous training. So in fact, you already automate these experiments that you can feed the data in your production service, and then there is a data validated, prepared for the model training, validating the model, the trained model, and deploying it in the model registry. So you prepare this machine learning pipeline, and this automates how the data is fed and the training is executed, and then the trained model is put in the model registry and then in the prediction service. So you develop this automated pipeline, but you only automatically deploy the model itself. And finally, the last level, when you deploy, when you develop this machine learning cycle, and you have full CI/CD to deploy the full machine learning pipeline, which is, well, the main differences. Here, maybe one point that when we talk, certainly, what is the essential component, at least at the level 1, then you have to monitor the model in production, and you need to get the trigger. For us, as I would say, that's the industry view, and sometimes for scientists, that if something changed in the data, maybe there should be some still human in the loop, a scientist in the loop, to look, okay, what's the real reason for that change in the data? Maybe there is some scientific explanation for that, and you want to catch that, and not just start the automatic retraining of your model. Well, that was the concept, but then you need to apply that in reality, and definitely you need then some tools, platforms, and this is just a small subset of whatever is available. And if you want to apply it in your project, then of course you have to evaluate all these different tools and platforms based on certain criteria. This is what we did in the beginning of the project, and this is one of our first deliverables. So it is in one can find in one of our first deliverables, but in the meantime we also submitted a paper, but that's about also changing the reality that with time things change. Like in the past, the mean average time to wait for evaluation maybe was few months. Now half a year you get nothing. So it is still under evaluation, but it was submitted. Then, okay, so for us, the criteria, first of all, we talk about only open source tools and platforms. Then different criteria which can be supported by the platforms and tools, orchestration, distributed training, code management, model development, and so on. So we evaluated all those according to this criteria. But also when you think of the design of your platform, then you probably already have certain software stack. And it's not necessarily that the best match is the one which supports everything, but the best match is what you need in your system. Just as a highlight, these are 16 different frameworks and platforms which were evaluated. Some of them kind of have overlap, of course, some of them actually complement each other, but they all have some open source version, and some of them provide also free cloud access. And that's, of course, not the same thing. So if you are happy with the free cloud access, you can be happy with the tool. If you want to deploy it on premises as an open source tool, then maybe the open source version is much limited. And that's what is actually for this number of cases happens. Then again, depending on your software stack, you may like the fact that some of them support Kubernetes, or you may say, well, this actually complicates my whole architecture. And finally, some of them are really bounded, like TensorFlow Extended is bounded to TensorFlow, and you want to support different deep learning frameworks. So you may say, well, that's not what I want. So just to kind of say, as already Alvaro mentioned, we then chosen MLflow as we needed this experiment tracking model registry, and this is one of the most popular frameworks with good support and good community. Then also already mentioned, you want to monitor also models in production, and the data and the model may drift, and then you need a certain drift detector to detect these drifts. And so you can then, there can be different types of drift detectors which support different type of drifts. Change drift, concept drift, data drift, or maybe you actually make an ensemble of these detectors, and depending on kind of combination of concept drift, for example, and data drift, and whatever happens, then you get you produce an alarm. And the data can be again streaming data. You kind of you have continuous streaming of data, or you get data in certain batches. And this is again from the article we submitted. Lizana, the next talk, is the main author. So these are few drift detector tools which we evaluated, and then different drift types. And again, as it was already mentioned, that the one which was developed within the project by IFCA is Rorro, and you see that it supports most of the criteria. Then we go back to this machine learning cycle, and just kind of now the perspective on what Alvaro already mentioned. We start with the data, and we have tools like Nextcloud. You put the data, you have CVAT for annotation. We also, as well, I kind of missed that. You also can add, as again, there was just discussion, you can get external data of data sets from external data repositories like Zenodo, and actually, as well as said, not only Zenodo. And yes, we offer, well, this is a cookie cutter symbol, but this is a templates hub where we provide templates to start developing your models. And this can be different scenario. You can also start developing of a new AI module for the marketplace, starting from already existing ones, or you can start from scratch in a simple way, or you may have already some machine learning code and you want to integrate it with things like DPass API, and then we have another template for that. And just to say that there is a demo of this templates hub at 1:30. It was, I think, scheduled 12:30, but I think it was moved to 1:30 today. Then, yes, we also support federated learning, and there was a demo yesterday by Judith. And as Alvaro presented, we have the full platform to do this development of model and development in using, for example, also development environment. MLflow is our machine learning tracking tool. I go on that on the next slide. Well, typically, you also, of course, want to test your software with like at least unit tests, and PyTest is the tool. And finally, many of the things are managed by Jenkins. Again, one of the open source tools where you can define pretty many stages for like publishing in Zenodo, publishing on the marketplace, deploying in the inference platform. So there is a new version of the model, tested, and then you are happy, you submit, you kind of do a merge with main branch, and then the pipeline starts and updates the model running in the inference platform. Oscar already mentioned several times during this conference, and again, Amanda presented it yesterday, and there was just a talk before coffee break. And then you can as well, so this is our drift monitoring tool, but what could be also useful, and this is now, say, work in progress, that every run of the drift detector can be stored in certain, say, general monitoring system, that you have a history of these drift runs, and you also store some metadata with every drift run, that if a certain drift is detected, you may go back and understand better what actually happened. And just a few highlights. So this is MLflow. MLflow supports at the moment just the basic authentication. It is a multi-user system. You may do it that all experiments of all users are shared, sort of seen for every user, or you can hide that the user sees only the experiments of himself. But what we also added, so we have now 2 instances, one running for EGI for EOSC, one for Imagine, and just another comment that this whole software stack is for sure is available, is also applied. So it's a part of EGI for OS software stack, and it is used as well in the Imagine project. So yes, we have 2 instances, one for EGI for EOSC users, the other one for Imagine users. Just need to use MLflow, and they don't need to install it themselves. Then they can self-register. The users of EGI for EOSC then can go self-register in EGI for EOSC instance, because this registration service, which we kind of brought additionally to MLflow, checks to what virtual organization we use as a authentication EGI check-in. So we check the virtual organization which user has, which is assigned in the ODC token, and based on that virtual organization membership, we can let user to register or not. And then you can also share, let's say, with some other user of the platform. You can share your experiments with different permissions: read, write, manage. Then one other point for MLflow is that MLflow has a support for large language models, and that's the next talk given by Lizana. And also MLflow is well integrated with the federated learning frameworks, at least like NVFlair, and that was also used in the experiments which were run by in one of the use cases, and there will be talk after next talk by Jaime. And yeah, some details that we have also monitoring of the MLflow and regular backups and garbage collection to kind of optimize the space. Then, as I said, here it's much greener than there. It's a typical CI/CD pipeline of Jenkins, and there is this stage to update the service in the inference system, like Oscar, just to highlight that. And then, yes, drift monitoring, the kind of typical 2 cases maybe is that you have a training data set and you want to have another version of this data set, or you want to extend it, which is anyway a new version. So you want to publish it. And before publishing, you may want to check if that new version of the data set drifted from the previous one. And that you can do with, for example, a combination of tools like data version control and your CI/CD system, again, leveraging Jenkins. And then you again want to enter this data, like historical data, into some system. Or you run the inference service in Oscar, and there is a new bunch of data uploaded by some user. And again, you may spawn in parallel with the inference service, you can spawn a drift detector, but again, you would like to enter that information, the results of the drift detector into a certain system. And that's what we are also working on, but as I said, work in progress, and we call it currently DriftWatch. So just some examples of historical data points, like, yeah, well, it's a test runs. So concluding, MLOps is a modern practice of automation, the machine learning cycle. And of course, there is a pretty many different tools already available and platforms with different features, and you really have to look what actually fits your case, and maybe still keep an eye on what is appearing, because there are more and more platforms, and previous platforms, they support more and more features. And I think I convinced you that in AI for EOSC, we already cover a good part of MLOps processes level 1, and well, that's it. Thank you.
Time for a quick question. No? Perfect. So we can switch to the next talk. I'm eager to hear from Lisana Berberi, or just new component of MLflow.
Okay, hi everyone. I'm Lisana Berberi from Karlsruhe Institute of Technology. Today I will talk about how to leverage MLflow for efficient deployment and evaluation of large language models. Okay, short outline about the key topics, so key elements that I will talk is, first I will start with a brief introduction on LLM, even though I think everyone here in the audience knows already. And I will continue with the new possibility, new functionality of the MLflow evaluation based on an existing deployment in the MLflow environment. And also continue with the comparison that we managed to provide with the two open LLMs that we consider. And at the end, so draw some conclusions and some future steps. So LLMs are advanced machine learning models designed to understand, manipulate, and generate natural language with high accuracy. Okay, maybe that's way. They are built using deep learning techniques, specifically using neural networks architectures and like transformers. So the specificity of transformers is basically this self-attention mechanism, and some utilized way of LLMs consider different applications: question answering, content generation, summarization, and decision making. So the showcase that we managed to implement is aligned with the question answering example. Some key characteristics of LLMs. Based on the scale and size, they are characterized by a very large number of parameters, often ranging from 1 billion to hundreds of billions. And definitely this allows these language models to capture complex language patterns and different nuances. And of course, the training data, so the data that they have been trained, of course, are considerably large amount of data. And the next generation, I guess, is the multimodal large language models, which they are trained not only in text-based data, but also a combination of the multimedia formats data like audio, video, and image. And of course, these data that these models have been training, they are coming from heterogeneous diverse data sources, such as book articles and websites. But definitely for the two LLM models we considered, actually it's not that we have enough information on these data. Some applications that are existing application right now are chatbots, content creation, code generation, and research and education. Typical examples, I can mention Llama from Meta, the GPT models by OpenAI, and the older, let's say, version of the LM like the Bird by Google. So to continue with MLflow, as Valentin already mentioned, and also Alvaro, we used MLflow in AI for EOSC project, and actually I used the MLflow development instance available in AI for EOSC project to showcase our implementation. MLflow, as already mentioned, is an open source platform, free and open source developed from the Databricks company, which it is designed basically to manage the whole machine learning lifecycle from data preprocessing, creating and building the model, training the model on different data, of course, tracking experiments, then packaging the model with all the dependent libraries, then share the model, also serve the model into production via an endpoint REST API. Here we will, let's say, tackle two of these two main components of the MLflow, which is the tracking of experiments and deploy these ML models locally in our VM virtual machines. But why we used MLflow for evaluating these open LLM models that I will show you in the next slides? Because MLflow is resource efficient evaluation. It allows to assess model performance on specific tasks without, ideally, without extensively deploying the model into production. And with the evaluate functionality that is available in MLflow, it will allow for a quick performance assessments using, of course, different metrics like accuracy score on a subset of data as well. And by logging these predictions and comparing them against the ground truth labels, of course, MLflow will help to identify areas where the model might need some improvements. And even, you can start with an existing, of course, OpenLLM, and you can query based on your data set, check if those answers are accurate as based on your use case, and if not, you can then fine tune, and then after fine tuning, of course, you can evaluate again. Instead of course, deploying models in a full-scale environments, which is quite resource intensive, and as you know, even to run inference on these, very small, considerably very small, let's say, based on the current developments, latest releases of the different LLMs, well, still is quite resource intensive. And the idea is that MLflow offers you the possibility to evaluate these models on sample data sets. So I will just mention the three actually metrics that we consider. These are built-in metrics coming from the TechStat library, and they are already building in MLflow. Yeah, we just wanted to show this first implementation, let's say, trial, but here in MLflow via the Evaluate library, we have also the possibility to create custom metrics. So you can create new metrics based on your needs. And so again, how do you want the performance, how do you want to evaluate the performance against which metric? The three metrics that we took into consideration actually are, so I can say the RE grade level and the Flash Kincaid grade level. Both of these are actually, they outputs a number from the range of 0 to 15, which approximate the grade level needed to comprehend the text. So basically, how easy is to understand specific text that you give, of course, as a prompt input. The latency as well was another metric that we analyzed during our evaluation. Latency, it's determined by the time it takes the model to generate a prediction, so a response for a given input. And of course, yeah, then we need first to deploy those models locally using MLflow model serve. It's pretty straightforward, I would say. Just follow the documentation that is available in MLflow how to do that. But in order to evaluate, then we need of course to use one of the main service that is being heavily developed actually, and is having quite an quite a big focus, I would say, from the Databricks company, is the MLflow AI gateway. Actually, this is still in the experimental phase. At least this is what is shown once you install it. And so this service is a powerful tool designed to streamline the usage and management of different language LLMs providers. And the idea is that via this interface, this gateway will provide you a unified endpoint to handle specific LLM requests, so to different LLMs that you have already deployed. You can start the service by executing this command, where you first definitely you need to install that, and you need to edit your configuration file where you add which are the models that you want to configure and against which models you want to run the predictions. So this functionality evaluation consists actually of three main components. Of course, you need to have the LLM model, and of course we are talking, so I'm talking here, sorry, for open LLM models. You need the model, and first you need to log that model into MLflow tracking server, and you get the model URI. And basically how this is done, it's quite straightforward as well, based on the documentation that is available in the Hugging Face portal. Then you define your metrics, so the performance against which metrics you want to measure, basically. As I mentioned, we considered like built-in metrics for now, RE grade level, Flash Kincaid, and the latency. And then, of course, you have the possibility to even log the data set during inference in the MLflow tracking server. And this data can be a pandas data frame, a Python list, or NumPy array. That is one of the instances in this dataset class. I will move on to just a short information on our setup. We had basically 2 virtual machines to implement our evaluation trial, and each machine has Tesla T4 GPU, 16 GB, some disk space and CPU RAM as it is here. Before moving to the results of the LLMs that we took into consideration, here is just an overview of the main features between the two LLMs that we considered. The Mistral 7B Instruct, actually version 01, and from Llama we took the 2.7B chat model. You have the references here in the slide if you want to read more about them. We tried to be fair in analyzing, try to compare like two models that were released maybe at the same time. What I found out actually is that for the Mistral, if you go to the Mistral AI website, it's a French company, which I guess, it was founded, I think in 2000, to begin in 2023 by some, I think, some people from Meta and also from Google DeepMind, at least what is given in the web. But what is interesting is for Llama, there are explicitly mentioned the numbers of GPU hours that it took to basically train from scratch this Llama 2.7B LLM model. But when it comes to the Mistral, basically nothing is mentioned. Even they do not mention if they use maybe Llama as let's say an original model, and then they of course used different other techniques than to do fine tuning or something else. You have the license as well, and here it is an example of actually how a prompt execution looks like using the AI gateway. I'm not sure, As you can see in this window here, so when you go to the MLflow tracking server, you have the possibility to execute a new run, and then you click prompt engineering. So this functionality actually in evaluating LLMs is done through the prompt engineering option, but as well, of course, you can execute it programmatically, and you can evaluate your models that are being served. As you can see in this served LLM model, there is this option where you can select which model you want to generate a response for, and you select one of these. And in the prompt template, of course, you can give some instruction, but you put basically, you need as well. So this is kind of mandatory to add a variable to the prompt template. And as an example, I just type, so just check what will be the response of this model when I type what is MLflow. And once you can click evaluate, it will show exactly the response of these two different models. And then you click create run, and these two runs basically will be available in your MLflow environment. I will go quickly. So beside this simple, let's say evaluation, we also try to evaluate these two LLM models, also considering two data sets like the Alpaca and the MVP data set, which is mostly basic Python programming. And just to show you how these data sets view looks like, basically we have an input. So exactly you give that input to the prompt template, and this is the ground truth labels, and this is output. So what is the output that basically was generated for the given input? Of course, as we wanted to have like faster evaluation results, we didn't manage to consider the whole data set, because this Alpaca, for example, consists of 15K records, and the other one, I think, is around 970 something. We wanted, just to show like a proof of concept for evaluating these LLM models, and that's why we consider only a subset, like 10 first rows from these two data sets. Okay, let's move next. I think I'm a bit over time. And here, yeah, you can see from the charts, there are the results that we managed to provide for the ARI grade level and the Flash Kincaid grade level for these two LLMs. But what you can see definitely, well, we can say that actually Llama is performing slightly better than Mixrel. But this is so just to be sure, both of these metrics consist that lower values are better, but with the idea that the lower means that is easy to read and understand a text, and they are not designed basically to measure the depth of reasoning, either the knowledge represented in the text. So basically they assess in terms of sentence complexity and length and the syllabus. And here for the latency, the third metric that we wanted to measure the performance against these two LLMs, well, definitely you can see that, yeah, from the graph, the Llama, of course, takes a longer time to generate a response, which in real-time applications, actually, this can affect the user experience, where so having faster, quick response is crucial. And if you go to the leaderboard in the Hugging Face portal, actually you have the possibility to to try to evaluate different open LLM models that are basically uploaded there. And so I just had a look, and you can see the Mistral AI than Meta. Here is the opposite. So greater is better, and you can see that, well, Mistral 7B Instruct actually is performing better in textual accuracy, in solving complex instructed questions than Llama. So to conclude, yeah, we showed why to consider MLflow to evaluate the pre-trained LLM models on a specific data set without providing a full-scale deployment. And as a next step, actually, of course, we plan to run the evaluation on these two full data sets, so two benchmarks, and then check the possibility actually to use. So now a new feature is LLM as a judge, where basically you can use the responses, the prediction that ChatGPT provides in order to assess how good your prediction of the model that you have deployed basically is doing. Of course, for that, definitely you need to have an open API key. And the other possibility that we still plan to investigate is to probably fine-tune our one of these open LLM models using the RAG approach. And why not then, if we are fine with the accuracy provided, then we can deploy this as a virtual assistant in order to support users to efficiently manage use the AI for EOSC platform. So that's it. Here are some references. Thank you.
There is urgent question, so we are a bit late, so otherwise we can discuss with Lisana in the break.
For sure.
Thank you, Lisana. So we continue our journey in the AI for EOSC with another interesting functionality that is for federated learning, right? Applied to the thermal bridging in urban environment.
Hi, everyone. Can you hear me? Okay, good. My name is Fahima. from Karlsruhe Institute of Technology. You may not recognize my name between these authors because my original name is Khadija, but since I want to make your life easier, you can call me Fahima. Today I want to talk about comprehensive study of two open source federated learning framework, MLflow and Flower, for detecting thermal breach in urban environment. Where is the next? How can I? This one, yes. Thanks. Yeah, as we know, machine learning, especially deep learning revolution, has many fields, especially image analysis or language processing. But these models are data hungry, and with more data, we may have better performance of the model. In the traditional training of the machine learning, we collect all the data and gather them in one central location, and then we train the model on this data. But and this method calls centralized learning. But this method may pose several challenges like data flow management, scalability, communication overhead, because of intense computation between industry. They are not willing to share their data, and most importantly, when the data are sensitive and we cannot share them. And we need to ensure that we are compliant with the strict data protection rules like GDPR. To address this challenge of centralized learning, Google introduced federated learning. In this method, multiple peers collaboratively learn a common machine learning model by exchanging model weights instead of sharing the sensitive data with each other. In the first definition of federated learning, there was a server that initialized a global model weights, and the server sends these weights to the data owners, which called here clients. Then clients start training this model under data, and then after training locally, they send back the model weights to the server, and then server use one aggregation algorithm to aggregate these local model weights and update the global model weights, and then server sends back these updated weights to the clients. Clients again start training. After this process continue until the global model weights achieve the optimal weights, or a number of predefined runs achieved. As I mentioned, this server use one aggregation algorithm to aggregate the local model weights. But in general, in the traditional distributed learning, it is supposed that the data comes from the same distribution, and the number of data, the size of the data set are almost the same in all the nodes. But in the federated learning scenario, we know that the data are maybe unbalanced and non-independent, non-identically distributed. To address this non-IID nature of the data in federated learning, several aggregation algorithm was developed. The first and the simplest one is Fed average, which use weighted average to aggregate the local weights. Then we have this FedProx that add regularization terms to the local function, local loss function to deviate the local weights of client to avoid the local weights of the clients deviating from the global model. Then we have Fed optimization, which is an extension of the federated average. Instead of using this simple weighted average, the server uses an optimization function to update the global model weights. A scaffold is also another aggregation algorithm which add correction terms to the model weights after each epoch of local training, again to prevent local model weights deviating too much from the global model weights. And in the literature is a scaffold. It mentioned that a scaffold is developed to use when we have uneven data set on each client. In the federated learning, workflow is the sequence of steps that we have to take to train a global model in distributed manner. We have different workflow in federated learning. The simplest one I already mentioned, that global model parameters are distributed to the client, and then after the local training, they are collected and aggregated based on one of the algorithms that I mentioned there. Then we have this cyclic weight transfer, which servers select a subset of the clients, and the first clients you can see in the first picture in figure here. The first client start training the model on its data, and then send the model to the second one train the model and send to the next one until the last client. The last client either send the model to the server, and then server broadcast the model to all the clients, or if we can remove the server and the last client can broadcast the model to all the clients. We have also swarm learning, which is used when the server is not trusted or is not reliable. In this workflow, one of the client is chosen as a aggregator client, and then client start training the model, and then send the weights to instead of sending to server, they send this weights to the aggregator clients. So these aggregator clients do the server job in the swarm learning. To compare the centralized learning with federated learning, we select one of the use cases from AI for EOSC project, which objective of this client is to identify thermal anormality in urban environment to improve the efficiency of energy-related system. They use unit to segment automatically the false positive thermal abnormality detection. For example, in the picture, car, a warm car can be detected as a thermal breach, but this model detect this car in the image and automatically remove this false positive, and so it's used to improve the result of thermal detection model. This use case was very this use case had potential for using for federated learning because the data set was collected from 2 cities in Germany named Karlsruhe and Munich, and moreover the number of data set in Karlsruhe was much higher than number of data set, the number of images in Karlsruhe's data set. In practice, if you want to train your model in federated learning manner, you have to choose a framework and convert your model, your existing deep learning model to a federated learning version. In this study, we choose Flower and MLflow, that both are open source, and as Alvaro mentioned, Flower is already integrated with the AI for EOSC platform. And yesterday, Judith, my colleague, demonstrate how to start the federated learning server on the AI for EOSC platform. And it's planned to add this also add this MLflow server as a tools in the AI for EOSC platform. We use our use cases and different aggregation algorithms that I mentioned here to compare the centralized learning with federated learning results. Unfortunately, except federated Fed average, none of these aggregation algorithm was implemented in the MLflow. So first, for the TensorFlow, for the PyTorch, they already had this implementation. So we first had to implement these aggregation algorithms in the MLflow, and in the new version of MLflow, our implementation of these algorithms are available, publicly available. Then we trained our model first in the centralized manner, and then with the federated learning scenario. And in our use case, we found that a scaffold can perform slightly better than other aggregation algorithms. But for training a scaffold, we needed more memory on the server, and it takes longer to train the model based on a scaffold algorithm. Also, in our cases, we found that federated learning can even perform slightly better than this centralized learning. That means where we train the model on all the data set. Then we also use Flower and different algorithms that I mentioned here. Unfortunately, a scaffold wasn't implemented in Flower for the TensorFlow, so we didn't have time to implement it. So we used the ones that was already implemented, and we found that in our use case, Flower can even shows slightly better performance compared to the MLflow, because we look at the source code and we found that there is a small difference between implementation of this algorithm in Flower and MLflow. To use different workflow that I mentioned here, we had to use MLflow because Flower doesn't offer other workflow except scatter and gather. And in our use case, we found that using cyclic weight transfer as an approach is very important. The order of the clients is very important and impact the performance of the model. That means if we train the model first on the Parcero dataset, which has less data, and then train the model on the Munich dataset, we have better performance than choosing the other order. And we also found that in swarm learning or in cyclic weight transfer, if we remove the server and the communication be just peer-to-peer, the training can be faster because there is no need to send the model to the server and then server send it to the client. And also we found that swarm learning is more stable than cyclic learning, cyclic weight transfers. That means in the swarm learning, we need less runs to reach the optimal weights for the model. Some insight from using Flower and MLflow, we found that using Flower is much easier than using MLflow, but MLflow offer some features that Flower doesn't. For example, MLflow offers privacy features or experiment tracking with MLflow, TensorBoard, and weight and biases. We also have this decentralized learning, that means removing workflow in the MLflow, but not in the Flower. And we also have orchestration in the MLflow, but not in the Flower. Fortunately, in the recently, MLflow and Flower announced their collaboration, and in the new version of the MLflow, we can start a Flower job using MLflow command line, and in this new version, we can use experiment tracking tools from MLflow to track the experiments in Flower. And some conclusion from our study. In our use case, we found that federated learning can keep up with the centralized learning, but even shows a better performance than centralized learning. Again, in our use case, we found that scaffold perform better than other aggregation algorithms, but we need more memory on the server. And when privacy is not a priority, for example, in research, Flower is a better solution. But if we want to have privacy tools, for example, in industry, we need to use MLflow. And yeah, maybe in the future, with the collaboration with these two, these two framework, we can use more features from Flower, from MLflow, like this privacy features in the MLflow. And thank you for listening. If you have questions, I will happy to answer.
So we can have a quick question in the meantime that we switch the presentation.
Thanks for the talk. Your main finding is extremely surprising to me, which is that the centralized learning model is less accurate than any of the distributed or federated one. How is that possible? And is it also true if we would take completely different example cases, or it's a unique finding for this particular use case?
This is a result from this use case because our guess is that we have in the Munich dataset, we had 700 images, but in Carcero dataset, we had almost 100 images. And we think that in the centralized learning, because the number of image in the Munich dataset is more than Carcero, the model bias through this dataset. But in the federated learning, we trained two different models, and these two models capture the features from Carcero dataset and Munich dataset, and then we aggregate this model. And this is one of the reasons we have better performance using federated learning than centralized learning. And yeah, if you have the same situation in your use case, maybe federated learning shows better performance than centralized learning.
Thank you. The next speaker, Saul Fernandez, will give us further details on what is under the hood on the distributed computing platform on the EGI Federated Cloud. Thank you.
Well, hi everyone, I'm Saul, and today I'm going to talk to you about the workload management system that has been implemented on the different sites, or in some sites of the EGI Federated Cloud. First of all, as a reminder of Alvaro's presentation, the AI4EOSC project will deliver an enhanced set of tools and services for the development of artificial intelligence, machine learning, and deep learning models and applications for the European Open Science Cloud, the EOSC. One of the main components of this platform is the workload management system, who manages the execution of the compute requests received by the different institutes of this EGI Federated Cloud. So a workload management system is a tool or platform designed to allocate, monitor, and optimize the distribution of tasks and resources across a cluster infrastructure to ensure efficiency, productivity, and balanced workloads. Kubernetes is one of the most widely used options in the market for container orchestration. But however, this tool has some drawbacks, like, for example, it has a complex ecosystem and could be challenging to manage it. Additionally, this tool was originally designed to handle a single cluster, not multiple or federated clusters. And moreover, Kubernetes was initially geared towards managing complex microservice architectures, which may add unnecessary complexity for simple applications. So when considering solutions for distributed computing, the combination of Consul and Nomad presents a highly effective and simplified alternative. Consul is in charge of creating the network between the different nodes and the different sites, and for handling the service discovery and registration to ensure seamless communication. On the other part, Nomad is the orchestrator, so it's in charge of, or it handles the job scheduling and resource allocation across infrastructure. First and foremost, simplicity is one of the key advantages of this stack. Unlike other more complex ecosystems, this set of tools provides a straightforward approach for managing distributed workloads. Additionally, there is native support for multi-data center deployments, which means that these tools were designed to simply handle deployments across multiple data centers, a duration limitation found in other tools like Kubernetes that were originally designed to be operated on a single cluster. And well, another notable feature of this stack is the task-based approach of Nomad, which simplifies the workload scheduling, making it easier for users to manage the deployments or create new jobs without the need for any other complicated configurations. So once given this little context, I'm going to talk to you about how our cluster is structured. The cluster structure begins with the deployment of one primary data center, which in this case is the EGI4EOSC. And well, this primary data center serves as a central hub, so any other secondary data center can join this one to create the federation, the federated cluster. For managing the network traffic uses both as a proxy and a load balancer, ensuring smooth service access and the distribution of requests. We have also created several namespaces for easily managed or organized the workloads and resources from different projects in an efficient way. And well, the minimum requirements for setting up a cluster includes having at least 2 nodes with public IPs. One is for the Consul server, so it can create the network across the different sites. And the other one is for the traffic node, so it can make service accessible from outside the cluster. Finally, there should be at least one compute node, GPU or CPU, to handle the actual workloads. Locally, within each site, the structure is organized as a LAN federation where both console servers and console clients, which are the compute nodes, can communicate with each other. However, across different sites, across different data centers, only the console servers with the public IP can communicate with each other. So in those diagrams, you can see how the communication scheme will look like in these situations. Here on the left side, there is this LAN federation, which is local to each site, to each data center, while both console servers and clients, the compute nodes, can communicate with each other. And in this other side, in the right side is this one federation, where only the console servers can establish this communication because they have the public IPs. So they create this federation across the different sites. At this moment, we have a production cluster deployed, which has 7 server nodes, 27 client nodes, with everything together adds up a total of 1,759 CPUs, 70 GPUs, and 16.7 terabytes of disk and 5.1 terabytes of memory. So now we have the following question, and is how can we deploy this structure? Well, there are 2 possible options available. We have the Ansible roles and the Tosca templates. With the Ansible roles, which are provided and maintained in our repository, the deployment process requires to manually create the node instance using OpenStack or a similar cloud provider. And well, the operations that are defined within these roles are, for example, creating a new cluster from scratch, which is primarily used for creating a new primary data center. You can also create the certificates needed for securing the communications between an existing primary data center and a new secondary data center you want to add to the federation. And finally, you can federate a new secondary data center, which means deploying this new infrastructure and joining it to an existing federation, to an existing primary data center. With the Tosca templates, the deployment process is a little bit more automatic, it's a little bit more user-friendly, because first, you don't have to manually create the node instance because they are created automatically with the Tosca templates. And in second place, the deployment is carried out through an infrastructure manager who provides a user interface, a graphical interface, making easier all the deployment. So, well, the operations that are defined within these Tosca templates are quite similar to the ones defined on the Ansible roles. So you can also create a new cluster from scratch, a new primary data center, and you can federate a new data center, a new cluster, by joining it to an existing federation, to an existing primary data center. So in this picture, you can see the workflow of this infrastructure manager for deploying a new cluster with the Tosca templates. As you can see, you have a graphical interface where you can select the kind of deployment you want to carry out. It will be either a primary data center, a new deployment from scratch, or either a new secondary data center and joining it for joining it to an existing federation. So you can see, once selected this kind of deployment, you can fill a couple of forms specifying the architectural parameters like number of servers, number of compute nodes, and this kind of information. Once done, the Tosca template will be populated, so the deployment process starts automatically creating this node instance and setting up a console and Nomad for the new infrastructure, for the new cluster. So to this platform, we have implemented several customizations to optimize the platform for the i4EOSC project. First, we have changed the way in which Nomad manages the Docker images. By default, Nomad deletes a Docker image once the job that requested it, that was using it, finishes. This can cause delays when multiple jobs or several jobs want to use the same Docker image because they have to re-download it every time. So to address this situation, we have modified Nomad so it now retains the Docker images, and for managing the disk usage, we have installed Docum. Docum is a tool that allows us to remove Docker image based on a disk usage threshold. In this case, the threshold is set to 50 gigabytes. This means that once this threshold is exceeded, Docum will remove one of the downloaded Docker images following a last recent use policy. We have also, there are also some training nodes, as Alvaro explained in the presentation. And well, these are specific nodes that are periodically pulling all module Docker images. These allow users to test a specific module in the latest version with minimum response times, with minimum delays. For console, we are ensuring that the internal console RAF status, one of the internal console status, is saved periodically. This is crucial because a node failure, a server failure, can lead into an unrecoverable inconsistency status. So to mitigate that risk, we are taking these console internal status snapshots periodically, and before each run of the Ansible roles, before each modification of the actual configuration. Lastly, we are working on a nomad job node migration. This is a feature in progress that will allow us to save the status of a running Docker container and resume it in another node, allowing for a seamless job node migration across the whole infrastructure. So for managing the lifecycle of the jobs, such as creating, querying, destroying them, we have implemented a custom API. This API allows for seamless interaction with the Nomad Job Management System, so users can easily interact with their deployments. There is also a dashboard that uses this API. This dashboard provides a user-friendly interface, so users can interact or modify their deployments without the need for directly interacting with the underlying systems. So with this dashboard, users can, for example, create and modify or delete a deployment with just a few clicks, so it's streamlining the entire process. And well, finally, before finishing, let's go with some quick conclusions. So due to its simplicity, we are using Nomad instead of other common tools in the market like Kubernetes, and we have implemented several customizations on this tool for better usability. There are also available 2 different deployment methods, as I told you, the Tosca templates and Ansible roles. And at this moment, there is already deployed a production cluster formed by 5 different data centers from across 4 different countries, which have around 50 scientific users. And well, finally, we are continuously working on improving the platform by exploring all the new capabilities of the tools that we have implemented, such as, for example, Console Mesh, which provides utilities for making a more fault-tolerant system. We are testing with InfiniBand. We are working on this Nomad Job Node migration I just talked you about, and so on. And that will be all for this time. Thank you very much for your attention, and it will be a pleasure to answer any possible questions you might have.
Thank you, Saul, to be on time. Quick question while we switch the presentation? No? Thank you again. So the next speaker is Angela Bianconi, and we have a use case, maybe more close to I imagine project, but it's not related.
Yeah. Hi everyone, I'm Angelica Bianconi. I'm a PhD student in Sustainable Development and Climate Change, and I'm also affiliated with CMCC in Risk Assessment and Adaptation Strategies. And I'm here to present this application on exploring the potential of graph neural networks to predict the state of seagrasses ecosystem in the Italian seas. Okay, so marine and coastal ecosystems and their ability to flow ecosystem services are threatened by the complex interplay between human-made and climate change-related pressures, and traditional machine learning models such as random forest, supervector machine, or MLP are useful to evaluate the pressures affecting seagrasses, affecting marine ecosystems, but they do not consider the potential spatial dependencies of the data. And for this reason, we started to explore these most recent graph neural networks models in the context of stressor evaluation. So GNN explicitly modeled the spatial dependencies of data points, so they could be suitable for the evaluation of stressors. So the main aim of this work is explore the GNN to evaluate the impact of pressures on seagrasses ecosystems, and also compare this model with the model that are usually employed in this field. So the case study is inside the Mediterranean Sea that is affected by several pressures, both endogenic, like nutrient load, shipping traffic, or coastal development, and also exogenic, like changes in sea surface temperature and sea level rise. And the most representative habitat and ecosystem of Mediterranean are seagrasses meadows, and we can identify them with their state, so the spatial distribution that is identified as presence or absence. And more specifically, the case study are the Italian seas, and with a bathymetry layer up to 50 meters, because seagrasses usually lives until this quantity. And the dataset was computed by involving expert domains. We downloaded several indicators from a different open source platform like Copernicus, EMODNet, or UNEP. And we homogenized the resolution of 4 kilometers, the spatial resolution, because it was the most common among these variables. And for each indicator, we computed annual metrics. So the temporal resolution is annual, and the reference year is 2017, because in this year, we have the most representative data set on seagrasses. So the method involves the comparison between benchmark models, so random forest, MLP, and SVM, and GNN models like graph attention network and graph convolutional network. And to apply this kind of model, we need to construct a graph. So we need to map indicators and seagrasses into a graph. So each pixel of the case study that is identified by latitude and longitude is mapped into a node, into the graph. And indicators, so pressures, are associated with each node as a feature vector. And each node is connected with the 4 and also with the 8 nearest pixel. So the dataset was split in train, validation, and set. So we applied a mask to each node, whether the node is a training, validation, or test node. And for models that are not directly applied to graph structure, the observation corresponding to training nodes were used to construct the training set, and the same procedure was applied for validation and test. And for GNN, we explored 2 kinds of training on the interior graph and also on subgraphs obtained with a weighted random sampling based on class distribution. And we also tested several architecture with different layer configuration. That includes a single convolutional layer followed by linear layer, and also with 3 convolutional layers. And this latter performs better. And we also apply this architecture on both the configuration of the graph, so with 4-node and 8-node connectivity. And the models applied to 8-node connectivity perform better and were used for comparison, and all compared models were optimized by hyperparameter tuning with cross-validation. And so we can see here some comparative results. So all model performs well in terms of accuracy, and we can see the GNN have the best performance in F1 score related to the presence of seagrasses. But if you look at some qualitative result, you can see here 2 kinds of map. On the left side, we can have the random forest map on the test set, and on the right side, we have the ZCN map on test set. So we have here the prediction, and white pixel are absence pixel, dark green pixel are present pixel, and light blue are right prediction. So for example, in the focus B, focus A here, for example, we can see that the prediction of a random forest is an absence prediction, but the true label was absence, and it is in the middle of a meadows. And we can here we can see that GCN has a right prediction, and the same behavior could be visible in focus also B. And also here we have a similar error, let's say, because we have the random forest prediction that is a presence prediction, but the true label is absence. And here is the middle of the white pixel, so the absence pixel. So this could be related to the fact that random forest consider each pixel in isolation without consider the spatial context, while GNN is able to consider also the influence of the nearest pixel. And for example, we can see that GCN do some errors on the border of the meadows. So we performed also a sensitivity analysis to see what are the primary drivers of both model. And we can see that even if they are in a different order, more or less the model consider as most impactful the same variable. So sea surface temperature, sea level rise as regard climate variable, and distances from the most important cities and rivers from what regard the human pressures. And this is in line with other study that consider the impact evaluation of stressor on seagrasses. And to conclude, we can say that the spatial context help us in improve the predictive accuracy of the model. And we can see that thanks to the graph structure, we can have an impact on environmental application because of the possibility to integrate spatial dependencies, but also temporal dependencies, and also domain-specific knowledge. So this is why in the recent year, graph neural network has some successful results in environmental application, like in urban pollution, also climate forecasting. So in the future, what we want to do is moving in a local scale, we want to collect more higher resolution data. So in this way, we want to build a graph not only based on the spatial dependencies, but also on the temporal dependencies, and including some variables like current that could describe the ecosystem dynamics. So thank you for your attention.
We have time for questions.
I have a simple one because I did not understand something.
Mm-hmm.
When you draw in the results, you have data points all across the Italian coast, but then you only focus on 2 or 3 areas. This is where you have real data about seagrass, or?
No, I have real data about seagrass for all the Italian peninsula. I focus it just on that areas because just to zoom in some errors, because I have high performances and the maps are related to the test set. So I have a few points to show you.
Okay. Perfect, thank you.
Thank you.
Just one more quick question. So we know from fluid dynamics that interior pressure, it can be determined not only by surface waves, but also by interior waves, internal waves of the water. Are you taking internal waves into consideration in your models?
Not really, because I working in surface water, because the seagrasses lives until 50 meters at least. So I take into account also the surface.
Thank you again. We have the last presentation of the session. Jiri Chudoba with his AI assistant user support, right? Or DocuBot.
So, good afternoon. I have the privilege to be the last speaker of the session. And since the lunch started almost 30 minutes ago, then I really thank you that you are still here. I'm going to present you our work about the user-assisted, AI-assisted user documentation, the product which we call DocuBot. This work was done by 3 people, me the defining requirements, doing the tests and asking for improvements, then Michal doing all the technical work, and Lukáš providing the hardware and doing the setup of the hardware and enabling us access to some better hardware which we needed for tests. So what was the motivation for this work? 2 years ago, we had to move our storage element from the solution from DPM to Dcache, and it was a new product for us. And the documentation is quite extensive. There are many releases of Dcache at the time, or there are still those past releases there. There is a Dcache book, there is a user guide, and there are release notes. So it was quite difficult to find the answers to our questions as administrators of the Dcache. So users can ask as well via Dcache forum, user forum. This user forum has no archives, so it was a little bit difficult, I mean, to check if the same question was already answered. So what we have done, that we tried to use this retrieval augmented generation solution and large language models to answer our questions about this. So what the implementation is that not only for the Dcache, but it is generic, that it can utilize online Git repositories as a source of information about the product. And we can as well add private information to the product. So in this case of Dcache, it was the private archive of emails to Dcache forum. And then we use LLM to generate answers. You already heard about Mixtral 7B, which was presented in the previous talk as well. But this is configurable, and this is what we have chosen this model because it fit in our hardware. There's as well version with OpenAI models available and via this API. And the only disadvantage is that you have to add payment method to use this API, but it's really very cheap. All our tests cost less than $10 US. So to process the question, we use vectorizer, and again, it's configurable, and we have chosen this vectorizer sentence transformers all mini LM. And for OpenAI, the vectorizer is text embedding free small. And the part of the product is the custom prompts and possibility to add more custom documents. So here, there's a schema I will have to skip because of the time reasons. How does it look like? I mean, for a user, for the user interface. Here you can see the whole page. This is a web page. So on the left side, you can define a Git repository. You can add one or more Git repositories, and then you can select which branches are interesting for you. And as well, you can upload additional files in as a text files. Then you can ask a question here, and here is the answer. So, for example, this question, there's a simple question about Dcache, and there's a generated answer. But for us, the most valuable output was these links, where the answer, which the LLM used to find the answer. So sometimes the answer was not precise enough, but thanks to these links, we were able to find immediately the answer in the documentation. So this was one example. There's another example more for the administrator point of view. How can I configure extruders? And you can see that the answer can be quite long. The important part is the configuration of this, because everything is configurable. So on the bottom left, there's this field, and you can use different temperature. Our default is 0.2, but it turns out that maybe lower temperature is better. And very important is the system prompt. So each user can change this prompt and define the behavior of the model and define how the answer should look like. So this is configurable via this system prompt. For the hardware, for our default model, it requires at least 8 GB of GPU RAM. So we use NVIDIA T4 with 16 GB of RAM. And we found that the used memory was a little bit more than 5 GB. But we use the quantization of the LLM to 4 bits, and in processing, we reserved 16 bits for processing. When we wanted to try a bigger model, for example, this Mixtral 8x7B, then we had to use a bigger, better card. We had access to NVIDIA A100 with 80 GB of memory. The response time of this is in seconds. And since we start to generate the answer almost immediately, then it's not a problem because the answer is generated and the user can start to read already the first sentences of the answer. But the response time, when we were trying to run this product on CPU only, it was many tens of seconds, so it was not usable in practice. So there are more examples here. For example, here I wanted to show that we use it for the Dirac product as well. And for the Dirac, you have to look in the repositories where pilot is, because it's a different GitHub repository, and the Dirac.git. And then you can select which branches, which versions do you use to ask questions. So here is a question: how can I control the maximum execution time for a job? And here is the answer. I have compared it as well to ChatGPT. When we started to develop this in spring this year, there was ChatGPT 3.5, and this product had no access to internet. But nowadays, with OpenAI's ChatGPT 4 Turbo model, which is for free as well, you can get access to internet. And so it's for public documents. It is the answer, I would say, is even better than what we got from the Mistral model. And it's almost immediate as well. So in summary, we have created this publicly available software, which can be downloaded from the GitHub and could be used immediately. The big advantage of this product is that the private documentation can be added, and you do not have to share it publicly with those companies creating those LLMs. On the other hand, we have to use dedicated LLM instance, and this is quite costly. So currently for tests, we have one running instance on our on this address for a limited time, and so it means that we use one NVIDIA T4 card almost constantly, even if it is if there are no users for it. So there is a possibility to use GPT models via this payment method, and since it is relatively the cost is relatively low, then for standard running, it would be probably less costly than to use our own hardware. The main point here is that OpenAI's ChatGPT, there were many improvements in the last half a year only. So we see that with our product, which was developed without any support from any big project and in a spare time of one student, then we are not going, I mean, to do any development for of this only. And what we saw as well, that it would be a very great useful if there is one LLM instance available for public, for example, within the framework of some European project, where we could use it like we use ChatGPT via tokens. So we could ask, I mean, those LLMs, and that would save us, I mean, this dedicating instance of LLM. So that's all from me.
Thank you. There are questions?
I have one. Have you considered to do further fine-tuning on, for example, Mistral with the responses you got and the feedback from the users? I mean, you ask a question and then the question can be answered okay or not okay. So you could even do a further fine-tuning on the model with the answers and the feedback from the users, and then continue with the RAG. I mean, closing the loop, not only doing RAG, but also fine-tuning, so you get an improved or updated version of Mistral, for example, or you haven't yet have a look at it?
We haven't done it. The tuning was done at the level of prompt and at the level of temperature, that we found that if we decrease the temperature, we may get shorter answers or less answers, but more precise. And as I said, for us, the biggest value was those links to the original documentation.
Thank you.
One, did you measure the effect of the 4 bits quantization? So you said you use the model, but we use the 4-bit quantization to 4 bits.
Yeah.
So did you measure the degradation of the model with that quantization?
We don't have any precise comparison of it, but the feeling of the user was the same. So it was good enough. I mean, this 4 bits.
I guess using a 16 bits would not be the same model.
Yeah, it's difficult, I mean, to compare even the answer, because what we wanted was the solution for some question. I mean, to find a solution for some question. And once you have it, then you do not, it is difficult to even compare. When we wanted to compare this Mistral 7B with Mistral 8x7B, it was mentioned here previously, I mean, how to compare two LLMs.
Sure. Thank you again. Time for lunch. I would like to thank all the participants of this session.